In this video, we're going to clone Ghidra, build Ghidra, debug Ghidra, get into those internals a little bit. Now, Ghidra kind of has a lot going on, so we're going to focus on a particular area, but it'll be a chance to build Ghidra locally and debug it with Eclipse and kind of get into those details. Some of the things we discuss in this video can be applicable to other debugging and development experiences. Like some of the techniques I would use with Windows debugging tools, for example. So you might get something out of this even if you don't have a direct interest in debugging Ghidra. But if you are interested in touching on some Ghidra internals, this is a video for you. Now, this video came about because I actually was exploring some Ghidra features. Ghidra has a feature called version tracking. I wanted to give it a test drive, see how it worked. And while I was testing it out, all of a sudden there was an error and I couldn't use the feature. And I thought to myself, hey, this is a great opportunity to build Ghidra locally and debug it and kind of see what's going on internally. And interestingly or coincidentally, the issue I ran into kind of touches on some of the technological things that we talked about in some of the previous videos. Okay, enough said. Let's jump into the video and get started. Okay, I'm going to download VS Code. Now, if you have your own editor, you're welcome to use that. Double click to install, going to accept. And I like to add these two. Okay, I'll go ahead and launch. All right, it's running, so I'm going to exit. Okay, next we're going to install Visual Studio Community Edition, and this is required if you want to follow the walkthrough exactly. So I'm going to download, and let's just go ahead and open this up. I'm going to say yes. I'm going to click continue. All right, I'm going to scroll down here and choose desktop development with C++, and I'm going to check that. I'm going to click install. Okay, Visual Studio is installed. I'm going to click skip sign on. I'm going to keep it on dark mode and choose the C++ development settings. And we'll start this up, make sure it's working. And it looks like it's working. Okay, very good. I'm going to exit for right now. And everything is up to date, so I'm going to exit Visual Studio Installer. All right, and we'll exit this, and we'll exit this. Okay, next we're going to install Ghidra. So let's look for Ghidra GitHub. And here we have a top search result. So we'll scroll down here to the steps. And we have the install steps here. So we need JDK 17, 64-bit. So let's go and get that. Okay, I'm going to select the operating system as Windows. The architecture is going to be x64. For the package type, choose JDK because we will need that eventually. And then I'm going to follow the instructions to spec, and I'm going to go with 17 LTS. And I'm going to choose the zip file option. Okay, it looks like it's downloaded here. They have a view checksum file. And look at this, they give you a really nice certutil command line ready to go here. So you can just grab this and copy this. So I'm going to choose to open the folder for the downloads here. And I'm going to right click and give myself a command prompt here. And I'm going to paste in that certutil command. I'll hit tab on certutil just to complete it with .exe. That kind of lets me know that it found certutil on the path. I mean, you don't really have to do that here, but it's just something I like to do. And then we're going to go here and set this file to be the zip file. So I'm going to tab until I get to the zip file that we just downloaded. And we want to calculate the SHA-256. So I'll hit enter and we have this hash right here. Let's go over here and see. Yep. Looks like it matches. Okay, now that we've verified the download, I'm going to create a folder that we're going to do most of our work out of, and I'm going to call that Ghidra Dev. Okay, and I'm going to switch to Ghidra Dev, and I think I'm going to move all the downloads that I download for this. I'm going to move those over here into this Ghidra Dev. So we have our JDK zip file here. I'm going to type in Explorer and a period to open up Explorer. Now I'm going to double click on the zip file, or you can just unzip it the way that you like to unzip it. And I'm just going to do a copy. I'm going to click back on Ghidra Dev, and I'm going to paste that directory to copy it from the zip file right here side by side with the zip file in Ghidra Dev. And I'm going to hit refresh, which is F5. And I'm going to go in here and we see that we're getting a nice folder right here off of Ghidra Dev. And in fact, I'm going to go in here to the bin directory, and I'm actually just going to grab this right now. And while it's still extracting, I'm actually going to go here to modify the path to include that bin folder. So I'm including the JDK bin folder right here in my paths. I'm going to click OK, OK, and close everything. And it looks like that copy operation completed. So what I'm going to do is close this terminal window, and I'm going to reopen a brand new terminal window in Ghidra Dev. And we should actually see like the Java compiler here on the command line. Wonderful. It looks like the JDK is installed, so we're all set there. Okay, great. We have the JDK installed. I'm going to close this. And the next step is to download a Ghidra release file. So we're going to go over here to releases. That's right here on the right pane. And I'm going to just click the high-level releases link. The following section instructs you to download Ghidra 11.0.1 public 2024 130.zip. And we do this as a way of being thorough because we're going to download that, install it, and observe the problem in a release installation. After that, we're then going to create a development environment where we will build 11.0.1. When you do this tutorial, if the zip file I just mentioned is no longer available for download, don't worry about that. Just skip to the next section. As part of that section, we're going to check out the branch for 11.0.1, and we're going to build 11.0.1, and we're going to recreate the problem with that development build as the next step after this step. This step is just a way of being thorough to show you the what if, like you're using the release build, you see a problem, and then you get an idea that, hey, you would like to create a development environment to investigate it. But by going right to the development environment to build it there and investigate it there, you'll experience the same thing as using the release build. This step of using the release build is just simply to be thorough, as if it were a real world situation and you were using the release build and you encountered the problem. And even though the release that we want for this walkthrough is 11.0.1, very soon it won't be the top result and it won't be the most current release. It might be slightly older. So if you look at this video sometime later where 11.0.1 isn't the top release here, scroll down on this releases page down here until you find 11.0.1. Then what you would do is download here to click this Ghidra 11.0.1 public file here. Now, the reason why we're downloading 11.0.1 is it's part of the walkthrough. So we're going to start with that version as part of the walkthrough. And it is essential, as you'll see in the upcoming parts of this video. What I'm going to do is I'm going to go over here to this terminal window, and I am going to tab here until we find the Ghidra release, and I'm actually going to move that so it's here side by side like with the JDK download. This will just allow me to reinstall things if I need to or get to the original zip easily, and I'm just going to put them all right here in this Ghidra dev folder that I created. You don't have to do that. It's just something I'm doing for clarity as part of the walkthrough. Okay, with Ghidra downloaded, I'm going to use Explorer with a period to open up the current folder. And I'm going to double click in the Ghidra download here. And I'm going to double click until I see the top level folder. So here's the top level folder. I'm going to go one up, and I'm going to right click on this top level folder. I'm going to choose copy. I'm going to go and click Ghidra dev and right click and do paste. And that will copy the Ghidra release folder from that zip file right here into Ghidra dev. While this copy is taking place, I can move that over here. I can click in this window for Explorer and hit F5, which will refresh this and show me this folder while the copy to the folder is taking place. I'll highlight this and double click in here so I can see what's going on. And there it is. It looks like it's all here. That's great. All right, there we go. It's been extracted. That's great. Okay, with Ghidra installed, I'm going to type in / and the folder name, and then I'm going to tab until I get Ghidra run.bat, and I'm going to press the enter key to start it up, and it looks like it's installed and it's running, and it looks like it found the JDK correctly. Now, if you choose to double click Ghidra run from Explorer, you might get this smart screen block. If you get this, you'll have to right click on the batch file, choose properties, and choose to unblock. If you have questions about how to do this or want to see more of a walkthrough on unblocking and Ghidra installation, you can see the intro to Ghidra video, which I will link in the description below. Okay, great. I'm going to actually create a default project here, and it's going to be a non-shared project. I'm going to put the project right off of Ghidra dev, so I'm going to type in Ghidra dev here, or you can just click the ellipsis and find Ghidra dev. So I want to create a directory called Ghidra work, so I'm going to hit the plus sign there on the folder, the create folder little icon up here, create new folder, and I'm going to type in Ghidra hyphen and then work, and I'm going to hit enter, make sure it's selected, and I'm going to click select project, and I'm going to name this project test version tracking. I'm going to click finish, and there we go. We have our project. All right, so I have my Ghidra dev terminal window open, and we have Ghidra open here with this test version tracking project. Next, I'm going to type in 2022 in the start menu here, and I'm going to start out Visual Studio. And I'm going to go to create a new project, and I am going to choose to create a console app, C++ Windows console. If you want to reduce the selections here, you can choose C++, and platform would be Windows, and project type would be console. With that selected, I'm going to click next, and it's going to default to a location here. I'm going to change this to Ghidra dev, and I'm going to choose to place the solution and the project in the same directory. And I'm going to call this console app, and I'm going to click create. I'm going to remove this boilerplate code here, and we can just remove this as well too. Now, believe it or not, for this particular walkthrough, all we need is this little boilerplate for starters. So I'm going to go up here and make sure that debug x64 are selected. And I'm going to go to the build menu, and I'm going to choose to rebuild the solution. And there it goes. It built our debug version, and it's right here in Ghidra dev, console app, x64, and right here at this location. Okay, I'm going to copy and paste this path here, and I'm going to right click and choose copy. I'm going to go over to our terminal window, and I'm going to change into that folder. And we can see that the app is right there. And what I'm going to do is I'm going to copy the console app to console app 2. So we have 2 copies. Now, these are 2 identical copies. They're going to use the same PDB file, but the reason why we have 2 is so that we can have 2 copies that are representing 2 different versions. Now, in this case, the versions have no differences, because our goal here with version tracking is actually not to use version tracking or to walk through and demo it, but to actually get in and troubleshoot an issue. So I'm going to go over to the Ghidra window here, and I'm going to click on the project, and I'm going to press the I key. And what you want to do is navigate to the folder that we're in here, the one that has the console app and the console app 2. So we're going to import both of these. I'm going to start with the first one, and I'm going to choose all the defaults. And I'm going to click OK. Okay, the first one has been imported. I'm going to press the I key, and I'm going to select the second copy, and I'm going to click Select to Import and take all the defaults. I'm going to click OK. Those 2 copies are going to represent 2 different versions of the binary. Now, for our purposes here, the 2 different versions happen to be the same, and that's okay. Okay, I'm going to double click on the first copy, and I am not going to choose to analyze. So do not click on Analyze. Click the X to cancel. Go to the Edit menu and choose Symbol Server Config. Now, we're going to add a directory here, but first I need to go and get that directory. I want to select this directory where the PDB is located. So as you can see, here is the PDB right here. That's the symbol file. If you don't know what a PDB is, you can actually see the intro to debugging video, which I will link to in the description below. I'm going to highlight here this path, and I'm going to copy this, and I'm going to go over here to the configure symbol server thing here, and I'm going to choose add a directory, and I'm going to just paste that directory right in there and click OK. So you can see we have the Microsoft public symbol server here, and then we have the directory that we just added. Now, when Ghidra does its analysis, it will be able to find the PDB for this binary. And it's best to have that set up first before you do analysis so that Ghidra can use the PDB during analysis if you happen to have it. So I'm going to click OK to accept these changes, and now we're ready to analyze this particular binary. So you can do the analysis by going to the Analysis menu and choosing this, or you can do what I'm going to do, which is press the A key and then just click Analyze. In the lower corner, you can see analysis is taking place, and when analysis is finished, I'm going to close this window. Okay, it looks like analysis is finished, and I'm going to close this and choose to save the changes. Now I'm going to load the copy of that binary, and in this case, I can choose to analyze it right away because we've already configured the symbol path. There's no need to do that here. It's already set up, so I'm just going to click Yes to analyze, and then I'll click Analyze. And we can see it's working here, and when it's finished, it will prompt us with these warnings. I'm going to click OK, and then I'm going to click to close and save. Okay, so we've imported two binaries. Now they happen to be the same, but we're going to pretend that they're different copies and that we're interested in doing some version tracking between the two. And so we're going to start that version tracking by selecting both. And then I'm going to right click and I'm going to choose Open With, and I'm going to choose Version Tracking. And what I'm going to do is make sure the original version is here in Source Program and that the copy that I made here is the destination program. You can click Swap if yours are in the opposite order. I'm going to click Next. I'm going to click Run Precondition Checks. Ignore these little warning symbols here. I'm going to click Next, and then I'm going to click Finish. Okay, so what it has done, and it's a little difficult to see because all the windows are kind of blocking each other. So I'm going to actually move these windows here. It's opened up a destination window here, and here is a source binary window. These are your usual code browsers, but they are participating in the version tracking. And back here, we have a version tracking window here. And as part of the strategy we're going to take with using version tracking in this particular scenario, we're going to start by choosing File here and using the automatic version tracking. Let's choose it. And it begins. Oh no. Now, I'm expecting this problem, and this is what we're going to investigate. We see that there is an exception here. Gee, I wonder what this is. Now, we can report this exception, or as developers, we want to dive in and kind of look at the internals and maybe see what the project's like as we try to build it and work with it. Sometimes that's a good way to find out if a project is something you might want to get involved in. Or sometimes you might just do it to build your chops a little, or to familiarize yourself with the source code, or just to learn. You know, there's lots of reasons. You might have your own personal reasons. Whatever the reasons are in this particular walkthrough, we're going to pretend we just want to install the dev environment and kind of look around and familiarize ourselves with it, maybe to get some more information so that we can create a really good comprehensive issue or report, that can just help out and contribute a little bit. Also, looking at some of the internal source code might help you understand a little bit about how the disassembler works. Sometimes you don't really know how you're going to be inspired before you go on an endeavor like this, but you just have some instinct that you'd like to build up your chops a little bit in a certain area. You just like to, roll your sleeves up and dig in there and see if you can help out a little bit and maybe improve your skills. And so that's the spirit that we're going to take here as we approach this. Okay, so let's continue on. So the first thing we're going to do is we have this exception with a stack here. And what I want to do is take this and copy it to the clipboard. And then I'm going to open up Notepad here, and I'm just going to paste this in here so that we have it. So now that we've saved this, I'm actually going to minimize this because we don't need this right now. I'm just going to save it, and I'm going to click OK on this. And I'm going to actually exit out of version tracking. And I'm actually going to stop Ghidra here, the one that we were running. That was the public release of 11.0.1. So we want to set up the Ghidra development environment. So I'm going to type in Ghidra GitHub, and I'm going to search for that. And I'm going to click the proper result here to get me to the GitHub Ghidra project. And I'm going to scroll down here, and we have install, we have build, and here is develop. So for develop, they tell you to follow the steps for the build instructions up here. So we have to actually do the build instructions first. So let's follow these build instructions. Now the first thing we need is JDK 1764-bit. We already have that installed. Then we need Gradle 7.3 or higher. So I'm going to do a control and click on that to open it up in a different tab. I'm going to click that other tab. And I happen to know that 8.6 does work for this walkthrough. So I'm going to download binary only of 8.6. And they have a handy verify SHA-256 checksum. I'm going to click on that, and it looks like they have a file here. So I'm going to do what I did for the other downloads. I'm going to go here to our folder. I'm actually going to go up to the Ghidra dev folder, and I'm going to recall the previous move command that we used to move the zip file. I'm going to type in Gradle star and dot, and that should move both of them here. And there they are right here. So let's actually cat the SHA-256 file. And sure enough, we have a SHA-256, which is located right there in the file. And we can use PowerShell here to do get file hash. And I'm going to type in Gradle to select the zip file. And then we're going to select the algorithm of SHA-256. And we see that we have a hash match, so we have a good download. I'm going to do Explorer and then a space and a dot. That'll open up Explorer. I'm going to go inside and double click on this Gradle bin, and we see there's an inner folder. Let me double click on that and make sure that that's the top level folder. And it is the top level folder, so I'm going to click the zip file again to go back up. I'm going to right click on the top level folder and choose copy, and I'm going to go up here to Ghidra dev, click in here and choose paste, and it's going to copy that folder from the zip file right here into the C:\Ghidra dev folder that we've been using. And there we go, Gradle is installed there. Now the last thing we've got to do is grab this bin folder here, copy that to the clipboard. I'm going to do edit system environment variables off the start menu and open this up to go to the path. And I'm just going to pop this in here as a path at the end, at the end of the path here. I'm going to click OK, OK, and OK, and we can close this Explorer window. And because we just updated the path, I am going to close this old terminal window now, and we're going to open up a brand new terminal window. And I'm going to change into the Ghidra dev folder, and I'm actually going to type in Gradle version, see if that comes up with anything. Looks like we got help here, and oh, I typed in version incorrectly. So let me type in version, and there we go. That should be 8.6, and it is. Looks like we're good. Okay, let's go over here and close Gradle, and let's look at the next requirement. Okay, we're on Windows, so we're going to skip this Mac and Linux OS requirement. This requires Visual Studio 2017 or higher. We already installed Visual Studio 2022, and we selected desktop C++ development, and that installed all of these requirements for us. So it looks like we're good to go. The next thing we're going to do is get Ghidra source code, but in order to do that, we want to install Git first. So I'm going to type in Control-T to open up a new browser tab, and I'm going to type in Git Windows and hit Enter, and I'm going to take the top result here. I'm going to choose the Git standalone installer for 64-bit Windows here. Okay, once that's downloaded, I'm going to click up here to start the installation process. I'm going to say yes, and here it goes. We're going to go through and create this folder. And I'm going to take all these defaults here. The editor that we want to use, I'm actually going to choose to use Visual Studio Code as Git's default editor. And let Git decide. Yeah, I'm going to just leave everything else default. I'm going to keep that as the default. I'm going to keep that as the default, and I usually select this here, but I'm just going to keep everything the default to keep this simple right now. And I'm going to go next. I'll choose the Windows console, and I'm going to keep that at the default, and we'll use the Git credential manager, and I'll leave those at the default setting and let that go. And then we'll choose all that and we'll install. Okay, installation's complete. I'm going to uncheck this box and click Finish. I'll click in this browser here to close that window, and I'm going to close that window, and we're back here at the Ghidra setup steps. Okay, let's go to our terminal window, and I'm actually going to exit from this, and I'm going to do Windows X here and choose Terminal. And I'm going to go into the Ghidra dev folder, and I'm going to type in git version here, -- version, just to make sure that it's on the path and installed, and it looks good. Okay, we're going to go back to the steps here, and we can copy and paste this, but I'm going to show you what I normally do when I'm on a project like this and I want to get the source code. I just go up here. You can follow the instructions and copy and paste it from there. It's the same link. I'm just used to doing this, and I wanted to show it to you, and I'm sure you guys already know all this, but I'm just going to do what I normally do. So I click there to copy that, and I go over to the terminal window, and I'm going to type in git clone, and I'm going to paste this in, and I'm going to hit enter, and this will retrieve the latest Ghidra source code. Terrific. Now I'm going to change folder here. So I change into Ghidra here, and we can see that this is the Git repo. I can type in Git status to just verify that, and it says that we're on the master branch. Yeah, I can type in Git log just to see, the top of the log there, and I'll hit Q to quit. Good, we have Ghidra source code installed. Let's go to the next step. Now we're going to do something special here with this repo in order to align it with the version where we observe this issue. Now we observe this issue in Ghidra version 11.0.1. So very often when Git is used, tagging will be used as a way of marking versions within the repo. So without even looking around, let's just look at the tags that are in the Ghidra repo here to see if there's any that look familiar. So we type in git and tag and we hit enter, and we see that there's a whole number of version related tags here. Let's try to look for the tags that have 11 within the string. So I'm going to say git tag, and I'm going to pipe the output of that to select string, and I'm just going to type in 11. And sure enough, we see that there's 1101 build. So I'm going to take that tag here and I'm going to copy that, and I'm going to say git checkout, and I'm going to create a branch with the same name as the tag, and then I'm going to sync that branch. I'm going to create this branch where its head or a tip will be the same commit as associated with this tag. And I'm going to paste the tag, which is effectively like putting the commit hash for the tag there. This will end up creating a branch that has as its head the commit hash of this tag. Let's run the command, see what happens. Okay, there we go. Let's look at the log here. And here we are in our new branch, and we can see that the head is pointing to the same commit as that tag. Now, we could have just checked out the tag, and that would have been fine too for our purposes. But I decided to create a branch so that we can actually have our own little branch for this particular version as needed. We don't really need it for our purposes right now, but it's just a nice little space that we create, and I thought I would just show that to you. Sometimes it is useful to have your own branch associated with some version as a starting point for some experimentation or testing. And now that we have a repo of the source of the version of Ghidra that we used, which exhibited the issue where we saw the exception, let's finish everything so that we can build Ghidra from the command line and also set up Eclipse so that we can edit and debug this particular version of Ghidra. So I'm going to click here to copy this Gradle command, and I'm going to paste it right in here. I'm going to hit enter, and let's run it. Okay, great. That command is finished, and we're going to go on to the next step here, which is to actually build this version of Ghidra from the command line using this Gradle command. So I hit the copy button, and we're going to paste this right in here, and I'm going to hit enter. And this will take a little bit, so I'm going to speed this up, and I'll see you at the end of the build. Okay, great. The build is finished. Now let's give it a try and just make sure it's working. Okay, I'm going to type in Explorer and it's build. Then there's dist. Let's go there. Here's a zip file with the build that we just created. Okay, and we are going to go and we're going to copy this up here. Just for clarity, I'm going to append our build, just in case it's something that gets confusing later or something will be clear now. Okay, I believe this is the top level dir in this. So let me open that up a little bit. And we're going to grab this and we're going to copy this up to the root here. And I'm just going to paste that in. Okay, terrific. Here is that directory. I'm going to rename this our build, or I'm going to append our build to the end of it there. So it's just clear that it's ours. Okay, now I'm going to go in here and I'm just going to run the Ghidra run in here. And it should start up a copy of Ghidra. And it does. And it shows here that it's a dev build. And there we go. That's our build. Okay, great. So we're able to build it from the command line. Okay, great. I'm going to close this here and I'm going to close this. Now let's move on to the next step, which is to set up Eclipse as an IDE for our debugging and editing and viewing environment for Ghidra. Okay, to set up Eclipse as an IDE, we go down here into the Develop section, and there's a section here, Advanced Development. In the Advanced Development section here, there's Build Instructions. If I click on this, it actually brings us right up here to the section that we just went through. So we've already done those steps, so we don't need to do those steps there. The next thing we want to do is install Eclipse IDE for Java developers. So I'm going to right click here and open this in a new tab, and we can look for Eclipse IDE for Java developers, and we will download the Windows x86 64 version. And we'll click here to download. Great, it looks like Eclipse is downloaded. I'm actually going to go to the command line here, and I'm going to recall one of our old move commands, and I'm going to look for Eclipse here. There's the zip file right there, and I'm going to move that from the download directory to the directory right above the repo, which is our Ghidra dev subdirectory. And now if we look at that subdirectory, we can see that Eclipse is right there. So I'm actually going to do Explorer and ... and that's going to give me an Explorer here at that top level Ghidra dev directory. Okay, I'm going to double click on Eclipse to find the top level directory in here, and there's Eclipse right there. So I'm going to go back to the top up here on the zip file. I'm going to right click on Eclipse and choose copy. Now I'm going to go to Ghidra dev, and I'm going to go in here and right click paste. And that's going to copy Eclipse from that zip file into our Ghidra dev directory. Okay, that's great. Eclipse has been copied to the directory, the Ghidra dev directory. Now, while I could put Eclipse on the path, it's just fine to run it directly. So that's what we'll do. Now, Eclipse came in a zip file that, of course, was not signed. So let's see if there are some hashes that we can use to verify the download. Okay, here we go. It's right here, SHA-512. So we have a SHA-512 right here. Let's actually double click, and I'm going to Control-C that to the clipboard, and I'm going to paste that right in here with a comment symbol at the beginning of the line. And now I'm going to do get file hash, and let's go back here and reference that Eclipse zip file. And the algo is going to be SHA-512. Hit enter on that, and hopefully, oops, I'll tell you what, let's do FL, I think. There we go. And we got 144, and we got a 377B there. So it looks like we have a matching hash there. Okay, great. Okay, next I'm going to take this Gradle prep dev Eclipse build natives command line. I'm going to copy that to the clipboard, and I'm going to paste it in the terminal window here. We're still in the repo directory. I'm going to hit enter. This is actually going to prepare the repo for use with Eclipse. Okay, great. The repo is prepared for Eclipse. I'm going to put this terminal window over here and clear the window. Okay, now let's start up Eclipse, and I'm going to hit enter here and start this up from the command line by just doing that. And when Eclipse first starts up, it's going to ask us where we want to put the workspace for the projects that we're going to be using. And it's going to default to a location underneath my home directory. I'm actually going to place this in the Ghidra dev folder, and I'm going to name the workspace Eclipse-workspace. After we enter the workspace location and name, I'm going to click launch, and Eclipse will start up here. So I'm actually going to move Eclipse over here to the right side of the screen so that we can see the Ghidra Eclipse setup steps right here. And one of the first things I'm going to do is go to Window, Preferences, and I'm going to expand this, click Appearance, and I'm going to choose Dark, and I'm going to choose Apply and Close, and it'll ask me if I want to restart. I'm going to click Restart to restart. And when Eclipse starts back up, it's going to prompt me for the workspace location. It will default to the last location specified. That's the one that we want. So we'll just click launch. Okay, that's great. I'm going to dismiss this welcome tab. We don't need that. And now we can follow these Ghidra Eclipse setup steps right here. So the first thing they want us to do is file import. So I'm going to go to the file menu. I'm going to choose import, and then they want us to do general existing projects into workspace and next. Then I'm going to click browse, and I'm going to go here and click on Ghidra dev. I'm going to highlight the Ghidra repo that we've been setting up, and then I'm going to click select folder. Then they want us to check search for nested projects. So I'm going to click search for nested projects, and we'll wait for these to be found. I'm going to go ahead and click finish. So you will notice that there are two pop-ups that appear here. Now, these are application modal dialog boxes. Application modal means that when the dialog box appears, you can't really click other areas of the UI until you dismiss the dialog box. So you'll notice they're both kind of the same dialog box, and if you try to click here, you can't really click here. So this is the most active or the last modal dialog box that appeared. Now, I don't use Eclipse all the time, and that's not to say anything negative about it. It's not an IDE that I use all the time. What I can tell you is that just as somebody who hasn't used it in a while, the last time I used it was quite a number of years ago. But when I see a prompt like this, I'm expecting that it's just going to lead me to setting up and installing things. Well, the first thing I'm going to do is just hit cancel on one of these, since they both seem like they're kind of the same. And I get the same result with either one. I'm just going to speed through this part here just to kind of show you something. It's just to kind of show you something that I observed here, but we're going to actually end up doing something different than just simply following some dialog boxes here. So I'm just going to click cancel on here. See, these both look the same here. So I'm just going to click cancel, and they both lead to the same thing. So we're just going to stick with this one dialog box here. Now you would think that you would just click here on show solutions and it would go and take you somewhere where we can install these things that apparently we're missing, these natures. If you click on show solutions, it takes you here, and it's not as though it's showing me some list that it's ready to go and install. It doesn't have those things that it was listing to me just now. So all those CDT natures are not like automatically selected. It's not going to install them. So that really confused me at first. Here's what I ended up doing. We're kind of actually going to put this aside for a second by clicking cancel here. I'm going to bring the IDE sort of front and center. So the first thing I want to do is just make sure that the IDE is up to date. So I'm going to click the help menu and I'm going to choose check for updates. Now that actually does find an update, and it's going down here. It's busy working, but it ends up finding these updates. I don't need to select anything because everything is already selected here. So I'm just going to click next, and I'm going to click next again. And I'm going to accept terms and click finish. And then down here in the corner, we can see there's an update taking place, and I'll click here to get some more detail about that update, and we'll wait for this update to complete. Okay, after it finishes applying the update, it's asking if I want to restart, and I'm going to click yes, restart. Okay, it's restarted, and even though I don't expect any additional updates, I'm just going to check for updates one more time here just to make sure there's nothing else to pull down, and there's no updates found, so we'll click OK. So what I'm going to do now is I'm actually going to go up here and I'm going to go back to the marketplace. Now, once at the marketplace, I actually tried typing CDT and then hitting enter, and I experienced an error. So I get this server 500 error when I try searching for CDT. So I'm going to click OK, and I'm going to go back to the marketplace. And instead of searching for CDT, I'm going to go to this all markets and just choose tools. And instead of searching for CDT, I'm going to go up here where it says all markets, and I'm going to choose Eclipse project. Once it finishes updating, I'm going to scroll down and look for that CDT C++ item. So I'm going to scroll down here, and you see there's Eclipse C++ IDE CDT 11.4. And what I'm going to do is click install on this, and it's going to go here, and it's asking for me to confirm these selections. They're all selected, so I'm just going to click confirm, and there's no licenses to review. I'm just going to click finish, and now I'm going to choose project and build all, and you can see down here it's doing some work. I'm going to click this to get some more detail, and it's asking if I want to restart the IDE, so I'm going to click restart now. Okay, it's restarted. There's a welcome page. I'm going to dismiss that because it's really bright, and we can see it's busy working away here, and there's actually some C and C++ indexer stuff going on. So it looks like it's doing some more work based on those updates we just added. Okay, great. The build has finished. Okay, I'm going to click this down arrow, and if you don't see any configurations here, you can click on Debug Configurations and click here and click on Ghidra, and you can click on Debug. And you can see it starts up Ghidra in the debugger. Okay, I'm going to exit immediately. And if you click this down arrow thing, you'll see it appears here in the history. Now, sometimes these configurations appear here by default after you set up the environment, but sometimes they do not. And so after the first run, you'll start to see these here. So you'll notice after we run that one time, we now have an option here, and we also have a run configuration here. So the run configuration will allow you to run it without the debugger, and the debugger configuration will allow you to debug it. Okay, so we've got Eclipse set up for Ghidra, and we're able to start the debugger. Now, let's go back to the stack that we observed the issue with. Okay, I'm going to maximize the Eclipse work environment here so we can take up the full screen. Okay, let's use the debugger menu and select Ghidra to start Ghidra up with the debugger. Okay, let's open up our project that we created earlier. So I'm going to do File and Open Project. And what you want to do is navigate to where the project is located, which is within the Ghidra dev directory in the subdirectory Ghidra work that we created earlier. Select the project and click Open Project. Okay, when it starts up, it has our existing setup. I'm going to actually highlight all these and I'm going to press delete and delete all of them. And we're going to recreate everything here. And that's because I want to go through all the motions of setting up the symbol path and everything and just making sure everything works with this new configuration and this new build that we have. So I'm going to highlight here and press I. I'm going to go to the Ghidra dev folder. I'm going to click console app, x64 debug, and I'm going to choose the first one and select import. I'm going to accept all the defaults. I'm going to click OK. I'm going to press I again. Going to select the second one, click select to import, and accept all the defaults. I'm going to click OK. Okay, they've both been imported. Now I'm going to start up each one separately. And for the first one, as we did before, I'm going to say no, I don't want to analyze. And then I'm going to go to the edit menu and choose symbol server config. So we can see our symbol configuration from before is not here because this is a brand new setup, brand new environment. So let's click plus. I'm actually going to add Microsoft's public symbol server. And then I'm going to click plus here and I'm going to choose directory and I'm going to choose the ellipsis here to browse to the folder where the PDB is located for the binary that we're going to import. And that would be underneath the Ghidra dev folder in console app x64 debug. And then from here, I'll do choose, and then I'm going to click OK, and we're all set up. I'm going to click OK. Now the analysis will actually load it up for us, but if we want to actually see if it's set up, one thing you can do here is go to the file menu and choose load PDB, and you'll see here a green check with the PDB at the location we just specified if it was able to find it. So it looks good here. We can click load here. The analysis process will load it as well, but there's no harm in just loading it right there. And now I'm going to press the A key to analyze, and I'm going to choose analyze. And when I see no more activity in the lower right and there's no pop-ups with any warnings or anything, I will click the X here to close the window and choose save. I'm going to double click on the second binary. Now, because the symbol path is already set up, we don't have to do that here. We can just say yes to the analysis question and analyze. And once analysis is finished, it might pop up with some warnings or not, and I'm going to click OK. And then I'm going to go up here to the edit menu, and I'm just going to choose symbol server config. And I'm just sanity checking that it appears here, and I expected it to, but I just like to do that. So I'm going to click OK. And I'm going to click X here and save. Okay, great. Both binaries have been imported. The PDB was found and used during analysis. And so those are all set to go. So let's control click to select both of those. And let's right click and choose open with and version tracking. Let's make sure the original binary is the source and the destination is the one where we appended a 2 to the name. You can click swap if you need to reverse them. I'm going to click next. I'm going to run the precondition checks by clicking that run precondition checks. I'm going to click next. You can ignore those caution symbols. And on the final page, I'll click finish. Okay, so we have two windows here. Here's the destination, here's the source, and back here is the version tracking window. With version tracking here, we can actually go and choose File, Automatic Version Tracking, and it's going to begin the process. Great, it hit the same problem here, and we can expand this out. Now, if you don't have a copy of the stack, you can grab a copy here. I already have the copy from before saved here, so it might be a good idea to always get the latest one that you have here, because that one might have slightly different line numbers if it's not the same source code. Now, we know we're using the same source code, but there might be cases where you're using a slightly different build and the line numbers might be slightly off or something. So if you're triaging something and you're working on something, weighing all things, while it may not be the biggest deal in the world, if you have a call stack that is connected with the source code that you're currently debugging, that's probably the best call stack to examine. Okay, so what we can do is let's examine the point where this error occurs. So the exception seems to occur right here on matchdata.java line 83. So what we're going to do is go over here to Ghidra, we're going to click OK, and then we're going to go back over to Eclipse. What we're going to do in Eclipse is we're going to go to Window, we're going to choose Perspective, and we're going to open the Debug Perspective. With the Debug Perspective open, we now have some toolbar items here which can be helpful while we're debugging. There's also some other things here, and we're going to get into these things as we work through this problem. So with the debug perspective active, we have some toolbar buttons here which may be helpful to us as we work through this problem. And there's some windows and things that we're going to be using as we work through this problem. The first thing I'm going to do is hit Control Shift and R, and I'm going to type in matchdata.java. And when I do that, you'll notice there's one result here, and I'm going to highlight that and choose Open. And Eclipse opens it up. Now let's go down to line 83, right? Because that was the line. And here's line 83. And we can see on line 83, and it indeed does throw an exception. Now let's set a breakpoint on line 83. We can do that a number of different ways. One way is to go over here into this column and double click, and you'll see it creates a little icon that indicates a breakpoint has been created. Let's double click again to make that go away. We've now deleted that breakpoint by double clicking it. Another way you can set a breakpoint is to right click over here and just choose toggle breakpoint. Okay, we can right click on that breakpoint and we can choose toggle breakpoint, which deletes that breakpoint. And yet another way to set a breakpoint is to put the cursor right here on the line where we want the breakpoint, and you can go up here to the run menu, and I do believe they have a toggle breakpoint here. And if you choose that, you get a little breakpoint indicator there, and you can actually double click that to delete it. Yeah, and yet another way is we can put the cursor on this line again and go up to the run menu, and we can observe that the shortcut key to toggle a breakpoint is Control-Shift-B. So we can dismiss the menu by clicking again on the line here. And I'm going to highlight this line and hold down Control and Shift and press the B key. And we see that we've toggled a breakpoint on, and I'm going to hit it again to toggle it off. So you got a number of different ways you can, set a breakpoint. I won't go over those again. I'll just say that I'm setting a breakpoint, and you can see what I'm doing on the screen here. But just FYI, you have a number of different choices here as to how you can set a breakpoint, and that'll go for some other commands. There's a lot of different ways to do kind of the same thing in different areas. So I'm going to go here on the line where the exception is thrown, and I'm going to double click there to set a breakpoint. Now I'm going to Alt-Tab back to the version tracker, and I'm going to choose File and Automatic Version Tracking so that we can recreate the issue again, or as they say in the industry, so that we can repro the issue, which is short for reproduce the issue. So let's hit automatic version tracking to repro the issue. Now what you notice here is it looks stuck. It doesn't show us the exception box, and that's because we need to go back over to Eclipse, and you can see that our breakpoint was hit. Now when they talk about a breakpoint being hit, it just means that the code was executing and your breakpoint was encountered, and the debugger went into a pause state for at least the thread which is executing the code where you set the breakpoint. So in this case, we can see that this is about to throw this runtime exception here because of some kind of memory access exception. Okay, let's examine the context. And for those of you who are kind of new to this, when we talk about context, we can mean a lot of things in software engineering. Context can be some kind of handle or structure that represents the information pertaining to some API or situation that relates to a number of APIs or a subsystem. In this particular case, when we're at a breakpoint and we talk about examining the context, what we mean is what's going on here in this area. The context is specifically this situation where some error took place. So context is a general abstract term here, and it is a way of referring generally to everything that is available to us in terms of evidence or information that can help us troubleshoot a problem. So one of the things we see here is a try-catch block. So this is the try portion of the block, and then there's a catch portion of the block. For those of you who are not familiar with try-catch, here's a 2-second overview on it. The try block contains programmatic code, source code, lines of code, that if there is a problem, the catch block will execute to handle the problem if it's applicable to the problem. The try block is basically going to contain some code. In this case, there's bytes equal AData.getBytes. If there is no problem with this line of code, bytes equals AData.getBytes, what will happen after it runs is the program will continue to run in the lines following below the try-catch block, or it will continue to run on the next line of code in the try block, but this try block only has one line of code. So as soon as all the lines of code in a try block execute successfully, the next line of execution will typically be after the try catch block. Now, there is a variation of this paradigm called try, catch, finally. We won't cover that here, but finally is just a third block that always runs no matter what happens, whether there's an error or not. And that just gets a little tangential for this discussion. So let's put that aside. So this is the line of code within the try block. It's bytes equals adata.getBytes. If there is a memory access exception while this is running, then this catch block will run and it will effectively be handling that error. If some other exception occurs other than memory access exception, what will happen is that exception will not be handled by this catch block, but it will instead be handled by some other block higher up on the stack. That's not relevant to our discussion right now. Our discussion is solely focused on the problem at hand here right now. And all you really need to know right now for this particular context that we're looking at, this particular situation, is that if bytes equals adata.getBytes is successful, then execution continues here at this line down here. If this line here fails with a memory access exception, which is the problem that we're seeing, then this line here will run. If there is some other exception that is not memory access exception, then this function will immediately exit and it will throw that exception to some other catch block, which is way out of scope here, higher up on the stack. And that case is not one that we're concerned with for the sake of this discussion. Okay, so we don't see anything in this line of code that directly can throw a memory access exception. So that means this exception is happening during the call to adata.getBytes. Let's examine adata right now really quickly to see what we can learn about what's going on here. Well, first of all, sometimes it can help to look at the stack. So if we look over here, we can see the stack for this thread, which is currently running. Each of these items here represents a thread that's running in this program. This is the thread where the error occurs. This is the stack at the time the error occurs. This stack is active right now in the debugger. This top line is the top frame in the stack. That's the frame that represents the location where we're at here, where this exception is handled. We can infer from this stack kind of what's going on here in a general sense in terms of what the program is trying to do. We can see that a version tracking task is running, and it's running some method here, correlate and possibly apply VT, which probably stands for version tracking here. We can see it's using a class called data match program correlator, and that class itself is using another class called match data. And the exception is occurring in match data's extract source hashes function. The extract source hashes function is this function here that we're in. So you can actually see the name of this function up here. That's the name of the function here, and these are all the parameters that get passed. Let's go through this function extract source hashes really quickly. It looks like it's accepting something called a program, and there's an address set view. Now, let's just assume, we don't know what these are. We may not need to learn more about them to dig into this problem, or we may need to. But what we do is we just start by looking at it and just kind of taking in the data. It's like what I talked about in the prior videos. It's sort of like a puzzle, right? We don't have to get overwhelmed by it. We're just exploring to see what it's all about. We're just taking note of kind of what we can infer by looking at some of the naming here and things like that. So we see our exception occurs here, and it seems to be occurring in some kind of loop which is iterating over program data. And so it looks like it's asking the program for its listing, and from the listing, it's asking for defined data within that listing. Now, even if that's not exact, generally speaking, it looks like it's good enough to kind of get the gist of what's going on here. And for each of these program data items, it's actually iterating through, and it's basically like it's getting the length, it looks like, of the data. So here's the length of this is 152. And it's looking to see if the data fits into some kind of size range. We're not going to worry about why it does that. We just, if it doesn't fit within this size range, it's not going to take this part of the loop. And it looks like it has a Boolean that it sets to true by default. and the Boolean's name is doHash. So I'm guessing down here, if doHash is true, it's actually going to create a cryptographic hash for the data. It's probably using a cryptographic hash because that might be a good way of comparing data areas of two different versions of a binary. Remember, this is version tracking. So if it gets all these hashes from one binary and gets a lot of hashes from another binary, maybe the hashes can be used to find identical areas or areas which don't match. So that's probably what's going on here, something like that, right? It's getting this information. And we notice that data is the current item in the iteration. So it has this loop here where it's saying, hey, if there's more data, come in here, and this next function obviously gets the next data item, and it assigns it to data. Data seems to be some kind of convenience variable, so it's easy to work with that locally here. And then it comes down in here and it tries to get the bytes from that data area. And if it's successful in retrieving those bytes, it'll jump down here and it seems to do some other things. We're not going to worry about that at this exact moment. All right, so generally speaking, we can infer from this that version tracking is calling this function to process the data available from one of the programs. And as part of that processing, it's looping through the different data areas. And for each data item, it is calculating a hash. When it encounters a particular data item, it's running into what we call a memory exception based on the name that the program itself gives to the problem. But what's actually going on is something we don't know yet. And while we're inferring kind of everything here sort of loosely, we don't really need to concern ourselves with what the caller is doing or anything right now at this point. We just kind of want to know, why is getBytes failing? And I think before we dig into that, we might want to learn a little bit about what data looks like. So we see that data happens to be a data, and that's a type, could be a class, could be an interface. Let's examine and see if we can find out some more about what data is. So if we right click here, we can see that there's some menu options, and one of them is to open the type hierarchy. So let's click on that, and we can note also that by pressing F4, we can achieve the same. So let's click to open the type hierarchy. Okay, so it looks like data is some kind of ancestor to all of these here. Let's actually highlight data here again and right click, and let's do open declaration, which is also, we can see that that's F3. So let's click to open declaration. So we can see that data is an interface. You can read more about Java interfaces if you want to. It's not really critical for us to continue to examine this problem. And we can see that the data interface extends code unit and settings. So let's actually highlight code unit, right click, and choose open declaration. And we can see that code unit is an interface as well. Now I'm going to hold the Alt key and press the back arrow, and that'll take me back to the prior location. And I'm going to do the same thing again, and it brings us back to the original location we were at with this data interface. So data is an interface. Let's actually highlight data and see what kind of information we get. Okay, so data is a DataDB. So if we right click here on data and we do open type hierarchy, which was already open over here, and indeed we can see that data is an ancestor to DataDB, and we can double click on DataDB in here. We can see that DataDB extends the code unit DB class, and we can actually right click and do open declaration and see that code unit DB is an abstract class. I'm going to hold the Alt key and go back here. So again, we see DataDB extends code unit DB, and it implements the data interface. Let's do Alt and go back. Now notice here, I'm kind of just getting a quick fuzzy idea of the lay of the land. What classes and interfaces are going on here. I'm not getting too deep down the paths here, just yet. Now, that's just my approach here. If you like going way deep down or something, then that might work well for you in some particular case. In this case, I'm kind of doing breadth first reconnaissance in a sense. So I'm kind of going wide and kind of looking at the periphery surface as we work our way into more of the details of this problem space here, or this context where this exception occurred. And the context of where this exception occurred involves these interfaces and classes, which I just kind of briefly went over. All right, if I go down here where there is the actual use of data, and we see it's calling getBytes. If I right click on getBytes and do open declaration, we can see that it goes to codeunit.java, and it goes to what looks to be a definition of a function within an interface. And if I scroll up here, we can kind of see that this is the code unit interface. I'm going to do Alt and press the back arrow to go to the code where the exception occurred. Another thing I can do though is hold the control key and hover over getBytes, and I can choose to open the implementation. That's the context specific implementation based on whatever a data happens to be, and a data happens to be a DataDB in this context. Now, before I click on open implementation, I just want to reiterate to be clear if it's not obvious. I'm going to hold the control key and I'm going to hover over getBytes, and I'm going to choose open implementation. And then we're going to go here to data component, and you can see that it highlights getBytes here in data component.java. So we can see in here that getBytes actually ends up calling something called parent.getBytes. And we're actually going to get into this with the debugger. I'm going to hold the Alt key and press back. Okay, so now that we're back here, let's actually just look at a data in the variables window. Now the variables window is going to show you all the variables that are currently active within this stack frame in the current situation right now, exactly where it is. You can actually add your own watches here and expressions, and we might get into some of that, but right now we're going to focus on the variables window. And what we're going to do here is we're going to expand a data, and we're just going to look at this. And again, we're going to take this kind of fuzzy approach. We know that this is a data item that comes from a program, or we're pretty sure of that. And so we're just going to see kind of like what it contains and, just look around, see what we can glean. I'm going to try to make this font a little bit larger here by going to Preferences, and you choose Appearance and Colors and Fonts. And then we go to Basic, and I think in here there's Text Font. And then I'm going to click Edit, maybe 16. Let's try 16. Okay, I'm going to go to Preferences again, and this time I'm going to type in var here and then highlight Variable Text Font and do Edit. Let's go to 16 there. Okay, then I'm going to type in Tree and select Tree and Table Font for Views. I'm going to click Edit, and I think I'll try 12. Click OK. Click Apply, and yeah, that looks okay. Okay, great. All the fonts are a little bit larger. Sorry I'm doing that sort of in the middle here of everything, but it was something that, I just kind of noticed it just now. All right, let's look at a data here. So in a data here, what we see is there's a data, it's a DataDB, and there's a thing called address here. Let's see what that's all about. So we open that up. Oh, and we see there's an offset here, and it looks like this is a number which is in decimal. One thing we can do with Eclipse here is we can go to Preferences. Up here, you can type in hex, and it'll show you this option, Primitive Display Options. And you can choose display hexadecimal values for byte short, char, int, long. I'm going to click apply and close. Okay, with that applied, you can now see that it not only shows the decimal value for offset, but it also shows in brackets here the hexadecimal value. So we see 1400, 1D, 1E0. Okay, that's interesting. So this is a data area, and it looks like this is the offset. Is there like maybe a size here? Oh yeah, look, here's length. So we have length right here, and the length is 152 or 98 hex. Okay, so that's interesting. And right here it says the data type is a StructureDB. Now we don't know for sure if that indicates data type, but very often developers will work to create reasonable variable names. And in this case, it does look like this points to some kind of data type schema of some sort. And it looks like this is a structure. Let's actually expand this and see what's kind of in here. We expand this, and there's a whole lot of stuff going on in here. But one thing that stands out is there's a name here, and the name is exception record. Well, that's kind of interesting. All right, now one thing we can do as we're collecting evidence and data relating to a problem we're investigating is we might want to create like a little text file where we can copy data that we capture so that we can reference it later if we want to. So one thing you can do with the variables window is you can highlight like a data, and then we can scroll down to the bottom here, and I'm going to include length, and I'm going to hold the shift key and click length here, and then I'm going to right click and choose copy variables, or you can do Control C. Let me go to my terminal window here, and I'm going to type in Explorer and dot, and I'm going to click Ghidra dev here, and I'm going to hold Control, Shift, and N to create a folder, and I'm going to call this Docs. This will be a directory that can hold our, little documentation files or anything like that. And I'm going to right-click here and choose Text Document, and we'll call this Notes. I'm going to right-click here and choose to open with VS Code. So I'm going to paste this in here, and I'm going to save it with Control S. And, we may or may not use these notes, but I find as I'm gathering little pieces of information, it doesn't hurt to copy some of it off. But generally speaking, we know we're running into an exception when we call getBytes on this A data. And it seems to be a structure of some kind from the program. And the structure seems to have a type called exception record. Okay, let's go back over here to Eclipse. So I think we've got enough initial data here. Let's try to debug the problem a little more deeply. So in order to do that, I want to set a breakpoint on this line where the actual exception occurs. Recall that this line here where we have our breakpoint is where the exception is handled, and that's after the problem occurs. The actual problem occurs during this try block here. So we're going to double click here on line 80 to set a breakpoint. And what we're going to do is we're going to press F8 to allow the program to continue to run. It's going to finish handling this error that we've been examining. Then we're going to recreate the problem again, or repro the problem again. And the next time that we try to repro the problem, it will break here at this line right here. Now, before I press F8 to continue, I want to show you something. Notice while we're at a breakpoint right now that the play button here, it looks like a play button. This little play button is the F8 resume toolbar button. So when I press F8 to resume the debugger, it's the same thing as clicking on that toolbar button. Now notice how this toolbar changes when I press F8. Now you can click here or press F8. I'm going to press F8, so I'm going to press F8. Now, two things happen. One is that the stack where the error occurred has disappeared, and we no longer see that the resume option is enabled. When the resume option is not enabled, it means we can't resume. And the reason why we can't resume is because the program is running. It's not at a break anymore. I think most of you know a lot of this, by the way, but I just want to cover this so folks who, don't do tons of debugging, like many of you probably do, can kind of follow along. Now, if we go back over to the program, we can see the error, the exception error, as we did before when we ran it with the release build. Now, the reason why this is displayed here now is because we hit F8. When we hit F8 or resume, that allowed the program to resume. The program handled the exception, and the way it handles the exception is to display an error box that shows you what exception was encountered. And we can click details as we had done before, and it's the same stack and everything, so I will close this. Now, it's very common when debugging a program to rinse and repeat. And what I mean by rinse and repeat is you hit a breakpoint, you investigate something, then you might hit resume, then you'll reproduce the issue again, and you'll trace into things and debug. Then you might hit F8 to resume. If you have a lot of breakpoints, you might hit F8 a bunch of times to resume. Then you might repro the issue again and rinse and repeat. So that's why I use the phrase rinse and repeat. And you're going to see that that's what we're going to do here. We're going to kind of iterate over and over again in the same area. And we're going to do that as a way of slowly investigating the issue, digging in a little further, calling out information as we dig into things, and so on and so forth. So I'm going to click OK here, and I'm going to go up here to the File menu and choose Automatic Version Tracking again. That's going to begin the process of reproducing the issue again. It actually won't reproduce the issue immediately, and you'll see why. We go back over to the program, and we have our new breakpoint, which is hitting right here on the getBytes call. Now there's a couple things to keep in mind. We had a breakpoint here after the error occurred before. When we hit the breakpoint here now, no error has occurred yet. And in fact, this point in the program may get called many times before the error is encountered. Therefore, the stack that we're seeing now and the context that we're seeing now and the frame that we're at on the stack here at this particular point in time may be unrelated to the one where the error occurs that we're investigating. It's important to keep that in mind when you start setting breakpoints before the issue occurs that you're investigating. And there's many different strategies to debugging things. That's just an anomaly of how we're investigating things here now. But it's an important thing to keep in mind because this can come up with other problems as well. So one strategy we can take is to go over here to our notes, and we can look at this offset, which is ending in 8384, and here it's ending ending in D1E0. So we can use those numbers to maybe go over here and hit F8 until we see those appear here in the offset. So we can see here that that offset here that's shown here and the hexadecimal number as well, neither of those match this number over here. So it seems that this is not the error. So if I hit F8, we're probably not going to hit the error. So let me press F8. And I press F8 and we just end up at this breakpoint again, which means that the last time it was successful and it went past this catch statement and it just continued on, and now we're back here again. And we can see that this offset again is not matching the one that we're looking for. So I'm going to go here and just press F8 again. And once again, we can see it's not, the offset we're looking for. Okay, I'll go ahead and press F8 again. Oh goodness, this is taking a long time to do it this way. So that's kind of a pain. So let's try to employ something that debuggers generally provide, which is conditional breakpoints that will help us break here at a point in time that we will find interesting, which is when that offset is there. So the value we want looks to be like adata.address.offset. So I'm going to go over here to the expressions window as a way of trying to figure out how to access that value. Now I'm doing this with the notion that I don't use the Eclipse debugger all the time, and I know how to use debuggers though. So I want to kind of see if Eclipse will do something that I've been able, that I can do with other debuggers. So what I want to try to do is say adata.address.offset. So I'm just going to go here. I'm going to click in the expression thing and type in adata, and I'm just going to hit enter so you can kind of see how this works. So adata is an expression, and then I can open this up and it kind of looks like what we saw in the variable window. So the next thing I want to do is try to see if I can access address. Now it says error during evaluation here. And that means it's having trouble understanding my expression here. Let's actually go down to this line here and put adata so we can just double check some things. So first of all, I'm spelling this correctly, so that looks okay. Now the one thing I ended up figuring out here is that the Eclipse debugger, at least in this expressions window, it seems to be honoring whether something is accessible given the scoping that it has from a Java standpoint. So if address is private, it's not really going to let me directly access it. Now I'm used to using debuggers like the Windows debugging tools and GDB, and those tools are very liberal in terms of letting developers kind of do what they need to do to get to the values that they need to get to. The main point here is to kind of show you the process that I personally went through, given that I use Windows debugging tools mostly. And here I am coming over and solving a problem, in Eclipse. I just need to get to the value that I want to get to, which is that offset value. And right now this expressions thing is not letting me get there. So what we're going to try to do is find out how we can get to address in an allowed way, i.e. by using like a public method. In order to do that, I want to investigate this data type to kind of find out where address is and how we can get access to it so we can get to the offset value. All right, so we know this is a DataDB, and one way I can get to that is by going to GetBytes and doing open implementation here, and I can double click on, let's say, we'll start with data component. I don't think it's here, but we'll start here. So I'm gonna go here and I'm gonna look for address here, see if we can find it. Looks like it's not here, so let's actually go to DataDB and let's go to code unit here. So I'm going to right click on that and right click on code unit and open the declaration here. And it looks like we have address here. So here's address. Okay, so let me right click on address and look for references. And let's look for references in the workspace. And that's going to produce some results down here. And we can see there's an API here called getAddress. And it looks like getAddress returns the address that it pertains to this code unit DB. So let's actually go back over here to our AData address and type in get address and see if that works. Oh, good. It looks like it works. Okay, so now let's append .offset and see if that works. And I know it won't. We're going to get the same thing. So we got to see if there's a getter here for offset. So let's go see what address is. And we can see that address is this address type. So let's right click on this and go here, and we can see that address is an interface, so that ain't going to have offset. So let's actually do Alt and back arrow. Let's actually go to the declaration of address, and that's here. You know what we can do actually? So over here in expressions, what you can see is it is a generic address. So let's actually right click on this and choose open actual type. Okay, so this opens up, generic address. And here's offset. Now offset's a long, so let's actually right click on offsets and type in references and look for references in the workspace. And sure enough, here we are, and we have some possibilities here. So let me expand these and see if I can, here's an API, getter here called getOffset. And probably we could have searched for this in the file, or maybe even assume that getOffset existed. So it looks like getOffset is here. Let's actually see if we can use that here. So I'm going to replace this with getOffset. And there we go. It looks like we've got access to our offset. That's terrific. Okay, so now I'm going to hold the Alt key and press the back arrow, back arrow, back arrow, back arrow. I'm going back to where our breakpoint is. Okay, great. We're back here to the breakpoint. Now I'm going to double click here and then right click and choose copy to copy our expression. And then I'm going to go over here and right click on the breakpoint and choose breakpoint properties. I'm then going to click conditional, and I'm going to paste this right in here. And then I'm going to go over to our notes, and I'm going to get the decimal value for the offset that we're interested in. I'm going to copy that to the clipboard and go back over to this expression window. And then I'm going to type in equal equal. I'm going to paste in the number, and I'm going to put a suffix L as in long. I'm going to click apply and close. And now what we have is a conditional breakpoint. So when this breakpoint is hit, the debugger is going to look at the condition, and if the condition is false, it's not going to break and it's going to continue running. If the breakpoint matches, it'll stop as though it's just a normal breakpoint. So with our conditional breakpoint set, let's go up here and we can click the resume toolbar button, or we can just press F8. So I'm going to hit the toolbar button this time. And it looks like, it ran really quickly, probably through several iterations or many iterations, and then it stopped here because the conditional breakpoint was true. And we can see it's at a breakpoint because this is highlighted. We've got a stack here, and the resume button is enabled, meaning we're stopped right now, and we have the option to resume if we want to. Now we can go back over to the variables window. We could look at some stuff in the expression window, but I'm going to go back here so we can look at the context in the way that we originally looked at it. And we can see that our offset does match, and that's pretty good. So what we know is that the problem is probably going to happen if we step into this. Now, since we have breakpoints and stuff all set up, and we can get back to this point pretty quickly at this point, what we could do is just hit F8 to resume and see if the error occurs. Let's do that. So I'm going to press F8. And the error does occur because you can see it hit this breakpoint down here. Now, this is part of that rinse and repeat I was talking about. I'm going to hit F8 to resume again. It looks like it is running because the pause little indicator is enabled and resume is disabled, meaning we can't resume because we're not stopped. And the pause, indicator on the toolbar is enabled because we can pause because we are running, we are not stopped. So now we can go back to the program and we can see the exceptions there. So we just click OK. And then we go to the File menu and click Automatic Version Tracking to run a repro of the issue again, to reproduce the issue again. It's running. We go back over to Eclipse and we see it's at the breakpoint. Because we have a conditional breakpoint here, we look over here and we see that the offset that we want is here. So we have a really nice system set up here to run to the breakpoint right away, right before the problem occurs. And we know the problem occurs because we just tested it out. So we have a really good kind of rinse and repeat kind of started up here. Okay, terrific. So now that we're at this place where the error occurs, let's step into this area in order to see what's going on in there. So really quickly, an overview on the keys that are available to us. So you already know we have resume, which is F8, and we also have some other keys, and they're all next to each other on the keyboard, and they kind of make sense, the ordering here in Eclipse. So F5 is step into. You can think of that as the most detailed step function in the debugger here, because it'll keep stepping into and kind of go into everything, and it will cover the most territory. It's the most detailed stepping that's available to us. F6, which is next to F5, will step over. That's less detailed because it will step over a function instead of stepping into it. Step return is similar to Windows Debugging Tools GU, which is to go up. Step return is kind of run this until you return. And then we have F8, which is like a full-on run. It's telling the thing to resume. And the program will run until it encounters the next debugger exception or event of some kind, which could be a breakpoint or an exception or any number of things which could stop the debugger, including program termination. So we're going to be using F5 and F6 and F8 quite a bit. So let's go back here to the debugger. I'm going to use F5 to step into the function where the error is occurring. We do F5 and we see that we're in the getBytes function. I'm going to press F6 to step over and step over and step over. And you might be saying, well, why are you stepping over all those functions? Couldn't they be part of the problem? I'm doubtful that's the case. Lock acquire is just some kind of generic locking here for these methods so that they're thread safe. I think it has something to do with getBytes and the core code, which is actually touching the data itself in some way. And that's just a hunch based on the context, right? Not all calls to getBytes fail, and it's this particular data area at this offset. So just using my instincts from past experience and kind of the context here, it's kind of obvious to me it's not going to be check is valid. That's some sort of validity check. I don't even have to know what it does, but yeah, I don't really think that's going to be the place. And frankly, if I'm wrong and I step over, well, it'll throw a memory exception and I can correct my assumptions. But right now it's kind of a safe assumption to just go stepping over stuff, because if you run into the problem, then you run into it. And if you don't, then, you can just keep stepping until you've run into the problem. All right, so I'm going to hit F6 here because I don't think get length is something we want to step into. And we can see we get that 152, makes sense. And we step again, we're creating some kind of byte array that's going to hold the results. And then we step down here, and I'm going to move this window over. And it looks like we call this function here, getBytes of get memory of the program. We pass it an address, we pass it, which seems to be an array, which is going to hold the resulting bytes that are returned. And it seems like this function returns a length value, perhaps the number of bytes that it retrieves. And it looks like it's saying, well, if you don't get the number of bytes that I requested, or that, oh yeah, we don't really request any length. So what we do is we ask this data area what its length is, and it's reporting to us that it's 152 in length. And if we don't get back the entire 152 in this function here, this function then assumes there's some kind of problem, and it throws the memory exception that we've been seeing. Now that's assumptive. There could be other memory exceptions, but it might be worthwhile for us to just step over this and see if we hit this throw statement, because we already have these breakpoints set up, so we can just do rinse and repeat. So let's step over this and see what happens. Oh yeah, we go right into this if statement. So the length we're getting back must not be 152. Well, I have 152 here. In Windows Debugging Tools, x86 debugging, I can just look at a register to see the return value. But this is a Java debugger, and I don't use it all the time. It's Eclipse. So one of the instinctive things I would do is, how can I look at the return value of the last function called? Well, lo and behold, just look up in the variables context window here and you see getBytes returned, and it shows you what it returned. So we can see there that it returned 32 bytes. So we got back 32 of the 152. And when we don't get back the full 152, this function's not happy and it's going to throw this memory exception. So let's step with F6 to see what happens. And it will exit out of this finally block here. So this is an example of a try finally block. So this try block is occurring after a successful acquire. So the lock for this class instance here is acquired first, then the try block is entered. The finally block always executes even if there's an exception thrown within the try block. So the try finally block is a great way to have a catch-all exit here where you can unlock the lock. If you didn't do this and there was an exception, the class would remain locked and other callers would block indefinitely. So what you see happening here is an error is occurring, and this thing is throwing an exception. Now this thrown exception is going to be caught by the exception handler that's one up on the stack. In fact, I can just double click here. That exception is going to be caught by this catch statement that we were looking at before. So let's go back to where it's currently executing by double clicking the top stack frame. And you can see it's going to unlock the lock first because the finally block always executes even if an exception is being thrown. So the finally block is going to execute all the time, even if an exception is being thrown. And that's what's happening here. So after the finally block, it will then go to that catch handler. Let's see. I'm going to do F6 to step, F6 again to step over the release. Then I'm going to do F6 to exit the finally block, and we should end up in that catch. And sure enough, we do. The catch block catches the exception, and it's going to throw it up even further up the stack. And further up the stack, it's going to display the message box that we see in the application. Let's hit F8 to run this through so we can do our rinse and repeat. So F8, okay, we can see up here, there's the pause button, and the disabled resume indicator means things are running because we can't resume when we're already resumed. Okay, I promise I won't repeat that again. So let's go to the program. Let's dismiss the exception, and we could do file, automatic version tracking, but this toolbar button here is the automatic version tracking toolbar button, and it runs the same command that this menu option runs. You can see they have the same icon. So as part of speeding up our rinse and repeat, we might identify these little shortcuts as we progress further in examining this problem. So what I'm going to do now is just simply dismiss that exception like I just did by clicking the OK box and then just clicking this toolbar button. And then without even waiting for anything here, I can Alt-Tab over to Eclipse, and boom, I'm actually already there at the point that we want to debug. Our conditional breakpoint has stopped it right where we want it to stop. We can actually see here that the offset is what we want it to be. Okay, terrific. So now we can hit F5 again. We're back in the same place, F6, 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 F6. We know if we do step over or F6 here, it's going to encounter the error, and we don't want it to do that this time. We actually want to step into the function here so that we can try to find that place. We can try to pinpoint exactly where this error is occurring and why it's occurring. We're going to press the F5 key to step into this function. Now we're in a function called getMemory, not getBytes. And the reason why is I'm going to go back to the second frame here that we were just at. This was the top frame before, but now it's the second frame. And that's because we called into getMemory. We're going to go back there, but right now I just want to come back to the calling point. And this calling point here is doing a program.getMemory.getBytes, and then it's passing these two parameters. So when we do step into, the debugger takes that very literally, and it says, okay, the next thing I got to step into is getMemory. And after it steps into getMemory, then it will step into getBytes. So it's going to step into getMemory. It's going to get the memory object or whatever that object is. We'll look at that in a second. It'll return back out, and then it will call getBytes on that memory object, because that memory object has a getBytes method, as we can see here. So let's double click on the top frame here to go back to where we were. This is a memory manager of some kind. Now, my font size, I'm actually not going to change the font size back right now. It's kind of messing this up. So what we can do here is I can expand out this, and we can just look for memory. It should be under M here, memory manager. And we can see it's a MemoryMapDB. We'll see that later anyway, but sometimes you like to see in the context, hey, what is this thing? And we can highlight this, and we can kind of see it's MemoryMapDB, but it's kind of hidden because the font is too large and this window doesn't resize here. Okay, let's hit F5 again to step into, but since there's no function here, step into is just simply going to step one, which means it'll step out and return to the caller. So let's do that. And it steps out. So we just got back from calling this. We now have that memory object. And now we're going to call getBytes on that memory object. And I'm just going to press F5 to step into getBytes. And here we are. We're in MemoryMapDB, and we're in the initial getBytes call. So if I highlight getBytes here, we can actually see that getBytes takes an address, a dest, a d-index, which is the destination index, and then a size. And it'll tell us down here, offset into dest to place the bytes is d-index, so that was correct there, that assumption. And then size is the number of bytes to get. Now, sometimes you don't get nice documentation like this if you're debugging in other tools, so you may make assumptions that you'll have to clarify as you actually get into the details of the code. So in this particular case, 0 is the assumed offset when you use this API, and the number of bytes to get is equal to the size of the destination array. So basically, this API is a way of calling this API where you're going to place bytes at the start of dest and the number of bytes you want to get is equal to the size of dest. If we double click to the caller of the stack here, we can see that we create this byte array here to be the length that we want to get. So basically, if we go back up here into the top frame, we can kind of see that this is a 152. Oh, actually, let's look at it here. So we can see here in the variables window that it goes to 151, 0 to 151. That's 152 elements. So the length is 152. It's going to put the bytes that it gets starting at dest for a length of 152. So we can just hit F5 to step into this. And now we're into some sort of like meat and potatoes of the getBytes for the MemoryMapDB class. Let's actually move this over for a second and examine this. So here are the parameters that we kind of understand here. This is the address. This is the destination for the bytes that we're going to get. This is the starting index for where the bytes are going to be placed here. We know that that's a 0, which means we're going to start putting bytes at the beginning of the caller's dest array. And the total size that we're expected to return is 152 bytes. So we come in here and immediately we kind of identify there's some kind of read loop going on here. While read is less than the size that's being requested, continue looping. So it looks like this is supposed to loop until it gets all the bytes that are being requested by the caller. However, it seems there's ways in which this can exit, possibly like if there's some kind of error condition or something like that. We're going to get into this now as we examine this. So now I'm going to start using F6 because I want to step in this function at a high level and not really go into other functions just yet. So I'm going to hit F6 to step over and step over. We're initializing some variables here. So numRead is how many we've read so far, and numRead is less than the size that's requested by the caller. So we're going to continue looping. Now this is doing add no wrap last read. So it looks like it's adding to an address based on how many bytes were last read. So it's taking this address and it's incrementing it based on the number of bytes that were last read. Well, this function initializes last read to 0, and it hasn't read anything yet, so last read equals 0, so this add will likely do nothing. Now, if we're curious enough, I can hit F5 to step in here and kind of just verify what this is doing. And it says if displacement is 0, it just is going to return this. So it looks like if you're adding 0, it's just going to return itself because it's not changing its value. However, if the displacement is non-zero, it will go and do something to actually change the address based on the displacement. So it looks like our assumptions about this are correct. So let's just F6 to go down. And now we're going to pass that with F6. Okay, so now we have an adder here, an address, right? Looks like some kind of generic address. This is our offset, I think, that we were looking at before. Yeah, this is the start offset that, we were looking at before. And that's the start address that it wants to get bytes from. Okay, terrific. It's now going to get a block for that address. Now we can step into that, but right now I'm going to step over that by pressing F6. And we see that we got a block back here. So let's look at block. Now block is a MemoryBlock.DB. So we have a MemoryMapDB, which contains MemoryBlock.DB items or instances. And it looks like there's some other things in here. Here's a length of the block, I assume. Looks like it's 200 hex or 512 bytes. And there's like a memory map here, and there's like a start address. And this start address looks like it is slightly different than the start address of what we're trying to read. We can actually look at that. Yeah, we're trying to read starting from this address, which is at 1E0, whereas the start of the block seems to be at 000. So that's interesting. It's a 200 hex length block, which means it goes from D000 to D200. Not only that, we're starting to read at D1E0, so 1E0 into the block. That's kind of interesting because if I get the calculator out and we say let's go to the hex calculator, and I'm going to go to hex here, and I'm going to type in 200 minus 1E and then 0. We come out with 32 or 20. And remember, that's how much we read before, and we couldn't read more. It seems like we're reading near the end of a block that only has 32 bytes from the point at which we're reading, but that we're trying to read 152. Now that's a little assumptive because we haven't traced through things. So let's look at this a little bit more to kind of see what happens. So let's press F6 to step over. Let's move this over. And it looks like there's a thing that's going to say, well, if this block is initialized or it's mapped, then go ahead and call this. Well, I tell you what we can do here is, why don't we just press F6 to step, over this. And let's do F6 to kind of loop in here and kind of see where the problem occurs. So we're going to press F6. and then I'm going to press F6 again, and we see that it reads 32 bytes, right? If we look at last read here, we can see last read is 32 bytes. So we can see it stepped over this and it read 32 bytes. You'll see last read right here, and we can actually highlight here and see last read. Okay, that's interesting. And we can see, by the way, that it reads starting from this address into the destination array, and the index that it will be loading the destination array is num read plus d index. Well, num read is what we've read, and we haven't read any, so it's 0, and the destination index is 0, so it's going to start reading and putting things at 0 in dest. What that means is, as this loop reads data, it will change the offset where it'll put things in dest. And that makes sense because it's reading and loading dest as it loops here. So this is the first iteration of this loop, and it's going to read, and the length it's going to read is the size that the caller wanted less what we've already read. So we haven't read anything, so our first read attempt is attempting to read the full 152 that the caller has requested. Now we stepped over this function. We could actually go into this, but right now, again, what we're kind of doing here is F6 to do a high-level recon at a particular function on the frame, and then maybe digging into frames as we want to. We don't want to get too detailed immediately because we might go somewhere and spend a lot of time, and it may be away from the kind of the big picture. So I'm going to hit F6 here, and we see that it's going to take numRed, and it's going to increase it by what we just finished reading here, which is 32. I hit F6 to step over that. We can see that numRed is 32, and we can see that lastRed is 32. We can see that numRed, which was 0 before, has been increased by what we just read, which is 32. So we're going to hit F6, and is numRed less than what the caller is requesting? Well, numRed is 32. Because we've read 32 bytes to date so far in this call of this function. Size is much larger than 32, so no, we're not done yet. So things will keep looping here, and it's going to go in, and apparently it's going to get some other block. And if we look here, this add no wrap, it increased the address by the amount that we just read. Because we just read a certain amount from a particular address, we now no longer want to read at that address. We want to read just after the portion that we just read. So this add no wrap increases the address by the amount that we just read. And we can see that actually, if we go and look at adder in here, we can see, if we pull this out, we can see that the address is at 1D200. So this address here, ADDR, which you can see is right here, it had an offset that ended in 1E0 before, but now the offset ends in 200, and that's because it increased by 32. It increased by 32 because of this call to add no wrap, which increased it by the value of what we read last. It's now going to call this getBlock function to get the block that is related to the current address. So it's going to get the block that's associated with this overall address here, including this offset. Okay, we're going to step over and let's actually look at this block, see if it's any different than the other block. Well, this block kind of looks similar. It has a much larger length. The other block was only 512 bytes. This one's much larger. Actually, let's step through here and see kind of what happens. Okay, so I'm going to press F6 and I'm going to press F6 again. Oh my goodness, we skipped past everything here. So what that means is something must not have been true here. This break executed and it dropped out of the loop here. So I did a step, so it just stepped over everything and kind of dropped down to here. So we can verify that by highlighting here. We can see numRed is 32. 32 is less than what the caller requested, which is 152. So if we step out of this function, we see that's going to return that 32 here, which is not going to equal len. Len is 152. And of course, 152 is not equal to 32. So that's going to throw the exception. Okay, interesting. So we now kind of know that the second block in that inner function there is failing for some reason. So let's go back into that. This is, again, the rinse and repeat. So we're going to hit F8, and that's going to hit this exception here, the one where we had our initial breakpoint. And I'm going to hit F8 again, and now the debugger is running. It's not stopped. We're going to go over here to the app. I'm going to click OK to dismiss the error message box. I'm then going to go up here to the toolbar to click the automatic version tracking, and that's going to begin our rinse and repeat. We're going to go over to Eclipse. We're stopped here. I'm going to hit F5. I'm going to hit F6 to go down to this line. I'm going to hit F5, 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 F5. And now we're into this function where we read the blocks. Okay, we read this first block here. And this block happens to be a, let's see, where's block here? This block is a memory block DB. Let's actually step down here, and you know what I'm going to do? I'm going to use F5, and even though this is not the problematic block, so to speak, I'm going to step into these isInitialized and isMapped functions to kind of see what they do. So I hit F5, and here's isInitialized. So isInitialized kind of looks at subblocks get 0 isInitialized. So what is subblocks? I'm going to right click on subblocks and do open declaration. And subblocks is a list of sub-memory block. Interesting. Okay, so there's a list of blocks. I'm going to actually do Alt and back arrow. And it's doing a get 0 to get the first index of the list. So it looks like it's getting the first subblock and it's calling isInitialized and returning that to determine whether the block itself is initialized. Well, okay, I can trace into here with F5, and it's going to do the get function in list, which array list, which we really don't care about. So we're going to do F6, and we're going to come out of here, and I'm going to do F5 to step into isInitialized. So let me go back up here in the stack. So I used F5 to step into get, and then I used F6 to quickly step out of get. And once we stepped out of get, I used F5 to step into isInitialized, which is being called on the object instance that's returned by get 0. And we can see that this is a FileBytesSubMemoryBlock, and its isInitialized is always true. Well, I might guess here that FileBytesSubMemoryBlock is some kind of block that represents bytes that perhaps come from the binary itself. We know that that's assumptive. It's not critical to verify that at this point, but let's just keep that in mind. We're going to press F6 to step out of here and F6 to step out. So since isInitialized returns true, and this is OR, it's going to short circuit and drop down here and do the get bytes. This is the first call on the first block here, which is going to return that 32 bytes. Oops, I accidentally did F5 to step into. One thing I could do is step out of, but I'm just going to hit F6 to come back to here, and we can see that that's the 32. Okay, let's hit F6 to step to the top of the loop here. And now we can actually look at this adder really quickly. Notice that this is the 1E0 offset here. So that's the 1E0 offset, and we are going to add 32 to that. So watch this value here as I hit F6, and you can actually see the increment take place to 200. So what we think is happening here is that both of these are returning false. Let's actually step into these for the problematic block. And once again, we can look at this block really quickly. Here's the block. This is the one that has the size of 1856. And here are the subblocks down here. Before we look at this further, let's just step into isInitialized. So I'm going to do F5, and here we are in isInitialized. It's going to do a get 0 to get that first subblock. So we can look at how many subblocks are here. There's, well, let's look at subblocks in here actually. We can go to subblocks is right here. There's only one, and it's a type of uninitialized submemory block. Oh, well, that's interesting. Let's actually step in to get, and now I'm going to do F6, F6, and we come back out. Now I'm going to do F5 to step into isInitialized, and wow, look, it returns false, and it's hard-coded as false. So it looks like an uninitialized submemory block is always going to return false. It will never be able to say that it's initialized, which means getBytes will never return bytes for an uninitialized submemory block. Now, we don't know yet really what an uninitialized submemory block is specifically, but it sounds like it's uninitialized memory, maybe, or something like that. Maybe this represents uninitialized memory as it's defined by the binary itself. It's kind of interesting. Well, that's an assumption we can keep tucked away. Let's actually hit F6 to step out and F6 to come back here. And I'm going to hit F5 here just to kind of see if there's any more detail to see. And I hit F5. Oh, it's calling isMapped, and that's because isInitialized was false. And because it was false, and that's an OR, if we go back here, we can see that there's an OR here, and this was false. So this couldn't short circuit. So it's going to try to resolve this by using isMap. So let's go back to the top frame here, and I'll do F5 and F6, F6. We come back here, F5 to step into isMapped. And it looks like isMapped is false, and I think this is going to be the uninitialized submemory block, right? Oh, interesting. This is isMapped of a submemory block, but let's actually go back to here. What is this? Okay, so this is an uninitialized submemory block. So let's right click on uninitialized submemory block here, and let's open up the declared type. And let's open up the type hierarchy. Okay, so subMemoryBlock defines is mapped, and it by default, I guess, defines is mapped as false. So where is that is mapped? Yeah. Okay, interesting. So we're already here, but I could actually do Alt and back, and it just brings us back here. Okay, so let's hit F6, and let's hit F6, and we can see here is mapped returns false. I'm going to hit F5 here to see if we get the detail of hitting this break statement. And it's obvious it does hit the break statement from the logic that we're looking at here, but I'm just curious if the Eclipse debugger will show us that detail or if it'll just jump down to here. So let's hit F5, and it just jumps right out here. So perhaps the way Java bytecode is structured, or the way the Eclipse debugger, interprets it, it seems like the break statement here is somehow kind of optimized where it just knows to jump down here when this logic fails to go into here. Very often with a debug build, you might get the detail of actually showing execution hitting this point. It's not a big deal because we kind of know what the logic is here and what's going on. Okay, so that's obviously going to return to the caller, and that's going to end up throwing this exception, and we can actually just go here. That's going to unlock, and I'm hitting F6 here, and we end up at our initial breakpoint. So I can hit F8. And the debugger is executing now, nothing is stopped. And I can go over here and do the usual dismiss of that error message, and then click the auto VT. And then we can go back over here to Eclipse, and we're at our rinse and repeat, conditional breakpoint, and we're ready to step in further and look at this a little bit further. Hey folks, I took a little break here, so if I look slightly different, that's why. It's the next day. I needed to take a little break. All right, let's continue. So we're here at our rinse and repeat breakpoint. I like that term, so I'm going to call that a rinse and repeat breakpoint. And you can have more than one rinse and repeat breakpoint. And so what I want to do is kind of go into where the problem occurs. So let's actually step in, and I'm going to kind of do this quickly since we know how to do it. So I'm going to hit F5 and F6 to go down here, and F5 to go in here, F5, F5, F5. All right, so now we're here where the memory blocks are, and we know the first one is not the problematic one, but let's actually look at that really quick, right? So, I actually stepped into all this stuff. Let me actually step out of this. This is going to get the block. It comes out. Okay, so here we are. Okay, it got the memory block. Now I'm going to open this up. Now the memory block is a MemoryMapDB. So what we might do here is let's actually get more of a visual of kind of what we're calling into and what's going on here. So let's go here to the stack point here where the exception is handled. That's where our initial breakpoint is. And we see that adata.getBytes is being called. Now that is a DataDB. So what we can do is put here DataDB.getBytes, right? So that's the initial call. And then inside that call, we have a call to the program member of DataDB. So DataDB, I hit F3 just now, and that shows us that DataDB has a program member variable, which is a program DB. So I'm going to do Alt and back space or back arrow. And so here we have program.getMemory. Okay, so that's being called within getBytes of DataDB. So this is a member variable, and we can actually maybe put program DB. This is just like a shorthand kind of quick ref for us to kind of get an idea of what we're doing here. Let's actually see what is get memory returning. Well, we can see that by going here. We can see here that there's this pointer, which is MemoryMapDB. We can just say MemoryMapDB. And what I'm going to do is I'm going to duplicate this line. And so what we end up calling here is getBytes on MemoryMapDB. Then we get into this function here. Now this function is going to call getBlock. And so what we're going to do is put this here, MemoryMapDB.getBlock, and we'll put adder here. So you can come up with your own way of creating notes that are helpful for you. I tend to just use something ad hoc on my own in the moment that works for the problem I'm trying to focus on. Of course, you can use all the IDE features to go and navigate around the source code. But when I'm working on a particular problem, I like to create my own little condensed set of notes that just show me all the classes that are involved and kind of who's calling who. It's just a kind of nice way of developing a picture in your mind of kind of the lay of the land. And I find for myself that table of contents or that roadmap, that high-level lay of the land, is very important to effectively digging deep in particular areas, because it kind of gives you an overview of the lay of the land, and then you can pick and choose where you're going to go. And as you dig deep in a particular area, you kind of know where you are relative to everything else. And I just find that that's helpful. So in this case, we have a DataDB whose getBytes is being called, and DataDB itself has a program DB. And so within this getBytes call, it's actually calling getMemory, and getMemory returns a MemoryMapDB, and we end up calling getBytes on that MemoryMapDB. And we can actually make a note of that here. We can actually just say this is effectively MemoryMapDB.getBytes. And in fact, we can actually say this is a programDB.MemoryMapDB.getBytes. I might as well just put programDB here, right? So this is programDB.getMemory, and it returns instance, right, like that. So we've got a DataDB whose getBytes is being called. DataDB has a programDB, which is the program member variable. It calls getMemory on the programDB, and that returns a MemoryMapDB instance. And then it calls getBytes on that MemoryMapDB instance. And so effectively what's happening here is DataDB.getBytes is being called, and then within that getBytes call, all of this is happening. A programDB instance, MemoryMapDB instance, getBytes is being called. Now, even though we're not really directly calling programDB dot and a MemoryDB, we are using a getter that returns that. So this is just shorthand that kind of helps me try to understand who owns what object instances and, you know, how things are kind of structured. And it sort of lets me know where I'm located. Okay, so here we are now in this getBytes call, and we call MemoryMapDB getBlock based on the address that we're currently processing. And that's this right here. So that returns a memory block, and we can actually add that to our notes. We can see the memory block gets assigned to block, and this is actually a MemoryBlock.DB. What we can do is update our notes to say this returns a MemoryBlock.DB instance. So we know in the problem case isInitialized returns false. Now we know that for the first block it does not return false. It returns true. And that's because the first subblock, which is at element 0, it's the first and only subblock, is a FileBytesSubMemoryBlock. And we can actually go here and type in block equals, and we can say iteration number 1 block is FileBytesSubMemoryBlock. Iteration number 2 block is. And so what we'll do is we're going to step forward here and go past the success case with this block, and we're going to go to the next block. And when we come around to this next block, let's expand this here. We can see it's another MemoryBlock.DB instance, but the one and only subblock that it has is an UninitializedSubMemoryBlock instance. So I'm going to go over here to our notes, and we can say UninitializedSubMemoryBlock instance. And we can say here fulfills 32 bytes of caller's 152 byte request. Not initialized fulfills 0 bytes, fails. And so we know that the program.getMemory.getBytes call ends up ultimately returning 32 bytes that were retrieved, and it returns that length of 32, and the caller doesn't like that. You know, it's getting less than what it asked for. The caller expects 152 bytes. It only gets 32, and it says, hey, this is a problem. We have a memory exception here. I can't continue. And it throws an exception. So I'm going to be a little verbose here and go down the stack. Here we are a couple frames down the stack, and you can see here, this is where it checks to see if this return count of bytes is 152. So it's supplying a byte array that's 152 long, and it's expecting the entire array to be fulfilled by this getBytes request. And as we know, it ends up returning only 32 bytes. And so we know 32 is not equal to the expected 152, and this is where the failure occurs. So let's go back up here. So we know that this uninitialized submemory block is not initialized. And so that therefore it returns false here and it's not mapped. So it basically can't continue and it returns with only 32 bytes having been retrieved. So one of the things I'd like to learn here is where does this uninitialized memory block, where does it come from? What part of Ghidra creates that? Why does it get created? And so what is its meaning and so forth? So let's try to track that down. One interesting way to track that down might be to go here and right click on the class name. Let's just go here and open up the actual type. So it says open actual type. So let's do that. And we can see that Eclipse brings us right here to the file where uninitialized memory subblock, uninitialized submemory block is defined. And we can see uninitialized submemory block extends submemory block. And we can see right here is a constructor. Well, one thing we can do is put a breakpoint right here on the constructor. Now, anytime Ghidra creates an instance of uninitialized submemory block, the breakpoint will cause the debugger to stop. And we can examine the context in which the class is being instantiated. And then what we're going to do is we're going to use Ghidra and see if we can cause this breakpoint to be triggered. If we cause this breakpoint to be triggered, maybe what we can do is augment the breakpoint to figure out which one relates to the block that we're concerned with. Now, one thing we can do is we can expand this uninitialized submemory block and we can look at its content. Now, as you can see here, we have a subblock length, which is 1856, and that just so happens to match the outer block length here of 1856. And so it almost seems like these outer blocks, which can contain one or more subblocks, will have a length that's possibly the total of the one or more subblocks. Since everything we're looking at right now only uses one subblock, we at least see there's a one-to-one correspondence there with the length. It's not a big deal for us to figure that out right now. It's just I'm showing you kind of what goes on in my thinking as I look at this. We also see something else that's interesting here. We see a thing called record, which is a DBRecord. Let's actually open this up a little bit here. Now, DBRecord hints to us that there is some sort of database that Ghidra uses. And we see some fields here in this record. We see field values. And so it seems like this is a record in a database, and these are the values of the fields of the record. We see a key here. That's probably a key for the record. And then we see schema. Now, schema is kind of interesting. That would be the definition, I don't know, maybe for the database, maybe for this record. Let's expand it and look at it. Oh, okay. Well, schema has field names. That's kind of interesting. Let's actually expand field names. Oh, we see an array that has these names of these fields. We see parent ID, type, length, starting offset, source ID, source address, and offset. Let's actually scroll up here and look at the record again. We see field values. Let's expand that. Oh, okay, another array. And look, there's 6 elements, 0 through 5, and the schema has field names 0 through 5. Let me expand this a little bit. So it looks like there is a one-to-one correspondence between the schema and the field values. Let's actually see if we can verify that by looking at the length. We know that the length here is a field name at position 2. That's the third field. So let's look at the third field here, or index 2, because it's zero-based indexing, right? So let's expand this. And sure enough, it's 1856 bytes in length, or 740 hex. So it seems that this is the length, and so that probably confirms to us that this is a one-to-one correspondence between the schema and the field names. It seems that this length is a good way to possibly identify our record and our block that we're looking for. So what we're going to do is we're going to resume Ghidra, and we're going to start using it to see who causes these things to be constructed, these uninitialized submemory blocks. And then we're going to try to see if we can find out which one creates the uninitialized submemory block for this particular block here. What I'm going to do actually is I'm going to select this entire area here, and I'm going to go down here and hold Shift and press the left mouse button. And then I select everything here. Now I probably can just do Control A in here, and that'll select everything as well. And then I'm going to right click and I'm going to choose copy variables. Now I'm going to tab over to our notes that we've been taking, from before. And I'm actually going to put a dashed line here and then paste in this new copy here. And then I'm going to press Control S to save our notes. And I'm just going to highlight this. We're looking for 1856. We're looking for the uninitialized submemory block that is initialized with a DBRecord that has a length of 1856. Okay, let's go back to the program here. Okay, with our breakpoint set here in uninitialized submemory block, let's go and run Ghidra. Let's resume things. So I'm going to hit F8. It catches the exception from the debug session we were just running. I'm going to hit F8 again. Oh, it's calling uninitialized submemory block now. That's interesting. Oh, well, let's just look at it and see where it's being called from. So this is calling to like clear cache and it's reloading. And let's actually see here, but this is the link that we want to look at, number 2. This length here seems to be for something else. And if we open up our field names, we can see that length is this third field here. And right here, the value is, 65536. That's obviously not the block that, we're interested in. So I'm going to hit F8 again. And oh, this looks like our block right here. So where is this being created? So we'll go over here to look at the stack, and we see that this is the constructor call that we're in right now. We're going to go up here to this MemoryMapDB adapter v3.create subblock. Okay, it looks like this can be called, and it's called with a record, and then it gets from the record the subtype column. Let's actually see what the value is here of subtype column. Well, they have 0, type column, length. So type column is the second column of the record. Let's actually do Alt and then back arrow. And let's expand this record. I'm just curious to look at this. Here's the schema. We expand the field names and we can see there's this parent ID, type, and then length. Now we were focused on length before. Type is the second element in the array. Let's actually go to the field values here, and we can see the field values have our length in this third field here. The second field here seems to have a code number of 3. So it seems that the type is 3. So you can see here it's asking the record for the byte value, which is in column, which is in the second column, which is the type column. And that value happens to be 3. So if we go and hit F3 on this, we can see that this is the second column. And we can see that it gets the byte value from the second column from this record. And that value happens to be 3. Then there's a switch statement, and we see that the case for v3 subtype uninitialized is being used. So I'm going to hit F3 on that. And you can see here at the top of MemoryMapDB adapter v3, there are a bunch of different types here which are defined with numbers, and uninitialized is 3. So that's another way of identifying our block. Its record will have a type of 3, and its length will have that 1856, I believe it was, that we had seen before. Yeah, 1856. So we have 2 pieces of information about the block we're interested in. It's an uninitialized block that's going to have a type of 3, which means uninitialized, and it's going to have a length of 1856. And if we want to, I can click here and hold the shift key and click here, right click, choose copy variables, go over to my little notepad, put in a couple dashes here and paste that in just to have a little scratch space here. Yeah, there is repetition between what we have up here and what we have down here, but that's okay. This is like our scratch notes area. And, we're just going to keep little bits and pieces of information as we want to. Okay, let's head back over to Eclipse here, and I'm going to do Alt and back arrow, back arrow. So this is the second frame on the stack. Let's go to the first one. So we are at this breakpoint. I'm going to go 1 frame down, and we are in this part of the switch statement because it's uninitialized. It's an uninitialized memory block as determined from the record itself. What this is actually doing is it's asking the record, hey, what type of block are you? And it's using that type to figure out how to create the subblock. So for a record in the Ghidra database, remember there's some sort of database here. We don't know exactly what that is, but I have an inkling, and we're going to get to that in a second. But there is some sort of database, and it has information about the binary that it's currently processing. And some of the information it maintains is about, how the memory is used in the binary. And for this particular subblock, there's a type here which is uninitialized. And what it's going to do is it's going to create this class to represent that block of memory. And it's going to pass it the record so that this block class here, this instance, can initialize itself properly. So what we kind of see here is that Ghidra has a database, and this database at least has some kind of table with records that maintains how memory is being used in some sense. And that record is then being converted into classes within the Ghidra space that Ghidra can kind of use to handle and manage the memory in a way that's efficient for the program. So it doesn't just simply get the record and keep that record sitting around. It takes the record and it's turning it into some classes and structure that's more convenient for the program's needs. All right, let's continue to dig into this. Okay, so we see that the uninitialized submemory block is being created here. Let's continue going down the stack here to kind of learn more about where this is happening. So it seems like there is a subblock table inside of this MemoryMapDB adapter v3, and the subblock table gets populated somehow, and it's basically iterating through all the DB records which are in the subblock table, and it's calling this create block or this create subblock function or method. Well, that's kind of interesting. Let me put the cursor on subblock table and press F3. That'll take me into this MemoryMapDB adapter v3. I'm going to right click on this subblock table, and I'm going to actually look for references to it. And we see that all the references are within this class, and that's because it's a private member here, so we would expect to find them in here. And I can go and start clicking on these to see where this is accessed. So we can see it creates initialized block here and populates it. We can see here it seems to delete something from there. We can see here, looks like this is getting the next key, and it's going to create a new record with a unique key. And then it's going to actually add the record to the subblock table. So the way that this database works seems kind of, sort of in a rough sense, kind of standard, where it's asking the table, hey, give me the next key. And we can confirm that maybe if it's obvious in here. Oh yeah, get max key, that's the highest value. And if the key equals the min value, then just return 0. And this forces it to start at 0 when it's set to the minimum value. It sort of seems like it's set to min value as an initializer to indicate no keys have been used yet. So in a sense, this looks like it's saying if no keys have been used yet, then start at 0. Otherwise, just use the next key that's available. So I'm going to hold Alt and go back. So this is creating a brand new database record, and it is calling get key to get the next available key. Here's the record. It's now setting all the fields in the record, and then it's adding it to the subblock table. So this is kind of an interesting function here from our perspective. Let's continue to look at the other ones here. So there's one here where this is, what is this doing? It's getting the record count, and this is doing something to get a subblock map. Let's keep going. This is actually creating the adapter. This is the constructor. And within this constructor, it's creating the table itself. Okay, that's kind of interesting. And then there's this thing called update subblock record right here. So the one that seems most interesting offhand, I mean, these potentially are creating something here. Where does this come from? Subblock record. It's going to create a subblock record, and create a subblock record is here. So it seems like even this one here, which was interesting, is actually, well, not that one, this one here. So it seems like this create initialized block actually calls create subblock record, which is this one here that we felt was interesting. So it's almost like if we put a breakpoint here, and I'll just right click here and choose toggle breakpoint just to make it clear. So there is a breakpoint here, and this is probably going to be called when it creates all kinds of records, because it doesn't seem to be solely dedicated to creating one kind of record. This will get called for creating any kind of subblock. But let's just start with a generic breakpoint here, and we can refine it with some conditions if we find that this is possibly a fruitful path of finding out what causes these uninitialized subblocks to get created. So right now we have several breakpoints all over the place. And one thing to keep in mind is that as we add these breakpoints, the debugger might be breaking at different locations, and we may not need to see those locations. Very often what I'll do is I'll keep a few breakpoints active. The debugger might stop at those breakpoints, but I'll just hit F8 to resume. And you'll see that we'll do that. And if we get too many breakpoints or a particular breakpoint becomes too noisy and doesn't bring us some value, I'll either delete the breakpoint, or if I feel I'll use it later, I'll disable the breakpoint. So we'll get to that in a little bit. If we go back up here to the top of this particular stack, to recap, we set a breakpoint here in uninitialized memory block. Now, if we go down here to these other frames, we see that this is being called by this function to create this uninitialized submemory block. And if we keep walking down the stack here, we can see the basis for creating that uninitialized submemory block is a record, a DBRecord. And this DBRecord has within it field values which indicate, first here, there's a 3 to indicate an uninitialized memory block, or submemory block, I should say. And then here is a length value of 1856. Now we've gotten a little bit further back. So first we were at the high level where the original problem was, and we stepped into a bunch of code to get a little deeper there. Then we got to a point where we saw that an uninitialized submemory block was connected with our problem in getting all the bytes we needed to satisfy the getBytes request. That led us to wondering, well, who creates this class? So then we put a breakpoint in uninitialized submemory blocks constructor. That's the breakpoint we're looking at now. That shows us that those classes get created, at least in this case, by iterating through some database records, where one of those records has a code of 3 for the type that indicates an uninitialized submemory block. And those DB records also have a length value as well, which affects the length value of the class. So the big question now is, who creates these database records, right? Where do they come from? What determines an initialized memory block from an uninitialized one? So what we've done is we've looked at this thing called subBlockTable, and we've looked to see who can add records to this table. What we did is we right-clicked on this and we said references and workspace to show us all the references to this subBlockTable. If we go down here, we can see those are all the references. And what we did is we found this particular method here, which looks very interesting. This method takes a bunch of different values and it creates a database record and it adds it to the subBlockTable. So right now we have 2 breakpoints that are not conditioned, one on the uninitialized submemory block. That's what caused this breakpoint that we're at right now to be triggered. And we just put a breakpoint here right now whenever something gets added to this subBlockTable. And what we're going to do is try to look to see who calls this method now. So as you can see, we're kind of digging deeper and stepping it backwards to kind of find the source of where all this information comes from that sort of drives us into the situation where we have the problem that we do. And what we're hoping to see is a big picture here of what creates the data that causes the problem, and why is there a problem, and what might the right fix be, or what kind of report can we create to open an issue. Maybe the Ghidra team could look at this if there in fact is a bug or a problem. Okay, so with our breakpoint set, let's hit F8 to run the debugger again. And right now it is running. It's not at a breakpoint, so we've gotten past all of our breakpoints. So what we're going to do now is I'm going to go over here to version tracking. I'm going to dismiss the error box, and I'm going to click this to start the tracking again, the version tracking. And let's go over here. And what we notice is it goes right to the breakpoint here that, this is our original rinse and repeat breakpoint, right? So this original breakpoint is the one that we were looking at before. And as we noticed, our new breakpoint to create the database record has not been called. So that seems to indicate that the database record must already exist. But what we're going to do is hit F8 to run this and see what other breakpoints get hit. If we get to the point where that uninitialized submemory block is being used and the database record didn't have to be created, it means that database record is already created and we need to do something to go further back in the process before that record exists. What I'm going to do is hit F8 here to run, and we can see it throws that exception error right here. And what we see is that the error is triggered. It hits our initial breakpoint, the very first breakpoint we had in the catch handler here. And what that tells us is it processed the uninitialized submemory block, and that uninitialized submemory block was created by using a database record. And the database record did not have to be created as part of this whole code flow, which means that it already exists. All right, so what I'm going to do is hit F8 here to run this, and we can see that it's creating this uninitialized submemory block after our error gets triggered. So this is creating this class as part of this reload all here. So let's open up the type field here, and we see it's a 3 uninitialized, so that's correct. And then we open up the size, and we see it's 65536. So 65536 is not the size we're looking for, but let's take a look at the stack really quickly. So if we look at the stack here, we can see that this breakpoint's getting called in this stack here that has program opener. So it looks like it's opening a program and it gets a domain object, and that leads to it creating a program DB, which itself then sets up these blocks here. So let's actually go down the stack here to kind of see what we can see. So we know these parts here, these are creating the classes. What we want to do is go here to, let's say where it's initializing this program DB. So this is the constructor for program DB, and this constructor is passing in this DB handle. Now, we don't know what the DB handle is, but it, sounds like some kind of handle to a database or something like that. So why don't we continue to go down the stack to see if we can discover what the handle is. So this is the caller of the constructor that we were just looking at. So we were just here in this constructor for program DB, and then I double clicked right below it here, and that takes us to this line here where it's creating a program database, or program DB. And that constructor for program DB requires this DBH, which is the database handle. The database handle seems to get created right here, just above the line here, where it says new DB handle. And in order to create it, it's passing it this BF. And the BF we can see here in the variables window is the local managed buffer file. Let's actually expand that to look at it a little more closely. So if we look at this, we can see that there is some information here, but there's a thing called file. Oh, this is interesting. Let's actually look at this value file. We can expand this open, and let me just highlight this. And boy, it's a kind of a long one. I tell you what, let's copy this. I'll do copy variables. We'll go over to our little notepad thing here, and I'll put a little dash there, and we'll paste this in. Well, it's referencing a file in the Ghidra work directory, and there's another subdirectory underneath that which has the name of the project that we created. So this is the name of the Ghidra project, test version tracking, if you remember. And it looks like there's a subdirectory called test version tracking.rep. And underneath that is some other subdirectory levels. And then finally, there is something like db.2.gbf. Just generally speaking, this kind of has the look of a file-based database that's sort of located and using the file folders here with some files. We see various names here that have DB within them and whatnot. So what I get from this information so far is that when we create a Ghidra project, we're kind of creating a database, and it seems like that database can hold all kinds of different information. Some of the information may relate to a program that you import into Ghidra. If you use version tracking, there might be database entries that relate to managing the version tracking sessions as you use them. Let's go back over to Eclipse here, and let's go back to the top of the stack here. And remember, we're looking at the creation of an uninitialized submemory block, and it's type 3, which is what we're looking for, but it has a length of 65536, which is not what we're looking for. If I go back over to my notes here, you can see that we are looking for, where is that size? We're looking for something that's 1856. I'm going to press F8 here, and we hit another breakpoint on creating an uninitialized submemory block. And if we go in here, we can see it's a type 3, which we expect. and then we can see the length matches the length that we're looking for. So this seems to be creating the uninitialized submemory block that relates to the issue we're seeing. Now there could be another block that is not the one that relates to what we're doing, which happens to have the same attributes. We could actually verify that really quickly by pressing F8 and seeing if we hit another breakpoint with the same length. Let me hit F8 and see what happens. I hit F8 and we seem to be creating another one, but it has 65536. Let me press F8 again, and we're now creating another one that has the same size, but actually if we look here, this size, oh, well, you know what's interesting here is let's actually go down in the stack here for a second to this program initialization. One thing I'm wondering about in the program initialization, we have two console apps. So if we look at the program DB here, so I'm in the program DB constructor, and if I expand this, if we go down here in the this pointer, we can see down here there is a name, and notice it says console app 2. That's the second of the two console apps. Now they're both the same binary, but from a Ghidra perspective, they are two separate entities. Even though they're a copy of one another, from Ghidra's perspective, they might be identical, but they're two physically different binaries, and we imported them separately, so they're going to have separate representation within Ghidra's database. So let's actually do this again, because we just kind of caught this on the second one that matched the link we were looking for. And my hunch is there's going to be two of these blocks that get created, but they aren't really like double blocks for the same binary. It's just that each binary has that block, so it's going to get created twice, once for each binary. So let's actually verify that by hitting F8, and let's get to a point where the debugger is running and it's not at a breakpoint. Okay, it looks like it might be running. Let me go actually over to Eclipse and see. Yeah, we are not at a pause right now. We are basically running. Okay, let's go back over to the program here, version tracking, and let's actually exit this again. And let's make sure, yeah, nothing is running there, no code browsers or anything. Let's actually double click on version tracking again, and that'll trigger our breakpoints. So let's head over to Eclipse here, and we see we are on uninitialized memory block. This is 65536. We're not interested in that, so I'm going to press F8. And here's the 1856 we're looking for. Let's actually go down the stack to the program DB constructor. Once we're in that constructor, we can actually expand, whoops, I made that scroll down. We can actually expand this pointer in the variables window, and we can go down here to name, and we can see down here this is console app.exe. So console app.exe is the first binary, and we can see for this particular binary it's creating a block that has this 1856. So let's hit F8 again, and we see 65536. Let's hit F8 again, and we see 1856 again. But if we go down on the stack here to program DB init, which is the constructor for program DB, and we go up and we make sure this is the this pointer, we expand it, and we go down here, we can see the name in this case is console app2.exe. Now I'm going to hit F8 again. And when I hit F8 again, the debugger runs and it does not break. So what does this mean? This means that we created two uninitialized submemory blocks with the size 1856. But each of those blocks seems to be created in the context of different binaries. So there's really only one time in which an uninitialized submemory block gets created of a length of 1856. I mean, it's twice, but for each different binary. So what we're trying to do here is we're using the length 1856 as a signature to identify the block that relates to the problem that we're seeing. And when I say signature, I mean that informally. It's data that we're using sort of in a fuzzy way as software engineers debugging something to try to determine if it's a good way of correlating that the block when seen from one perspective, i.e. when the problem occurs, is the same block that we see somewhere else in the program, let's say when the database is being loaded or created or whatnot. And what we've determined is that per executable or per console app, there is only one of those 1856 blocks. And that's good. It means that when we see that, we're looking at the one and only block of 1856 that pertains to a particular binary. And since our original exception is occurring in a context where it's processing one of the binaries areas of memory, those data areas of memory. If we can find an 1856 block that gets created somewhere and added to the DB, that will probably be a reliable way to understand how the problematic block gets created and what meaning it has to Ghidra and to our problem, and perhaps to how the issue might be fixed. What we also notice here is we didn't see the database being populated at all with this 1856 record. It's as if the database already has it. So we want to try to find out where the database first gets that uninitialized submemory block of a length of 1856. There's two possibilities here. One is we missed where it gets created somewhere in the context that we've been looking at. Another possibility is it gets created and added to the database somewhere else, probably beforehand, before we ever even create the version tracking. So it doesn't matter if we're wrong. Let's just make an educated guess here and start looking there. And if we don't have luck in that first place that we look at, we can always adjust and go back to maybe where we thought we might have missed it or something like that. So I feel a good first avenue would be to do this. Let's highlight all three of these items here and press delete. And we're going to delete everything from our Ghidra project. I'm going to say OK and OK. Oh, actually, we actually have to go here and close this. I'm sorry. So let's close this. All right, so we have closed the version tracking and all the browser windows are closed. So now I'm going to highlight all of these, press delete, and I'm going to click OK. So now I'm going to press I and I'm going to select the first console app and I'm going to click select to import. Now I'm going to accept all the defaults. Now keep in mind our Eclipse breakpoints are active right now, and you can notice in the background here, it has paused on import file and we hit some breakpoint back here. Let's go look at that. So we go back here and we see, oh my gosh, look at this. It's actually creating a subblock record and it's putting it in the subblock table. Well, we kind of know how to interpret these records. Let's expand this in the variables window. Let's look at the schema here to see what it's doing. And let's actually look at the field names. And this is a parent ID, type, length, and so forth. And let's look at the field values here. Whoops, field values. And let's look at number 1. Okay, so that's a type of 4, which is not uninitialized. We could actually go and look for what the codes are, but we know that we're looking for 3. And we can actually open this to look at the size. We're not interested in this block because we know 3 is not the right block. We're looking for a type 3 and a size 1856. What we can do is put a conditional breakpoint here. Before we do that though, let's see if we need to make that effort by hitting F8 a couple times, and who knows, maybe there's not that many blocks and we'll hit the block that we're interested in. Okay, so even though this record is not the one that we're looking for and this is not the right type, before I press F8 to continue forward here, there's two things I want to mention. Number one is we can consider putting a conditional breakpoint here for the attributes we're looking for, which is a block record of type 3 that has a length of 1856. In other words, we can turn this breakpoint, which will happen all the time, instead of it being hit every time it's encountered, we can add a condition. And the condition can be based off of these attributes, the type being 3 and the length being 1856. We can also just hit F8 a few times to see if a condition is even necessary. If we hit the block we're looking for right away, then we can save some cycles. Instead of making a condition, we can just hit F8 a few times. If we have to keep hitting F8 and there's just tons of blocks, then a conditional breakpoint might make sense here. Another thing we can do, even though we haven't found our block, even though this is not our block being added to the subBlockTable just yet, we can take advantage of this moment in time, this context here, and we can look to see what's going on the stack here to kind of learn where this happens. There's two reasons why that might be advantageous. Number one, generally, we can educate ourselves about what's going on here. Number two, there might be an easier way to place a breakpoint for the block we're interested in by using something further down in the stack here, which might be helpful to us. Right now, I'm liking the idea of setting a conditional breakpoint here, but I also want to peek on the stack here to kind of see what these other frames are doing, just to educate myself right now about the context and what's going on here. So for those of you with observant eyes, you've probably noticed on the stack here, there is a class called PE Loader, which is being used. And if you recall, from our recent videos, we've talked about the PE executable format. And we know on Windows, like console app.exe and console app2.exe, those are both PE executables. In fact, one is a copy of the other. But from Ghidra's perspective, they are two separate PE executables. And so then you might glean that Ghidra has this PE loader to help it load in PE executables. You might also infer from this, and this is a little bit off topic, but you might also infer from this that Ghidra has this concept of a loader and that perhaps it has different loaders for other platforms. Right now we're focused on Windows and PE executables, and that happens to be exercising the PE loader portion of Ghidra. So here we are at the top of the stack here, this top frame, and we're adding a record to the subBlockTable. Now, it's not the subblock that we're interested in, but we have a hunch that our subblock that we're interested in will get created in this same function, probably as part of this same stack. We'll find that out in a second. For now, what we know here is that Ghidra is using this PE loader class to actually seemingly process the PE executable. And as part of processing it, it has this method here called process memory blocks. I'll double click on that. And if I had to infer something from all this, and it's not such a leap to make this inference, it seems like this is the part of Ghidra that consumes an executable from the outside world, and it turns it into database abstractions, which it maintains within the Ghidra database. This is probably a way architecturally for Ghidra to maintain things within its application space in as generic and abstract a manner as possible. This allows for a lot of versatility within Ghidra in a platform-independent manner to at least some extent, if not a significant extent. I say this without a lot of in-depth knowledge of what's going on in Ghidra yet, right? Because this is our first time we're actually using Eclipse to kind of get a feel for what's going on within Ghidra. But putting on our software engineering hats and thinking about good architecture and whatnot, and kind of seeing things from some of what seems to be the good design going on in here, we see a number of abstractions and things to kind of represent uninitialized memory blocks and other memory blocks, and we see uses of databases. And so all of this kind of points to this notion of executables or binaries or let's say firmware or whatever being digested or taken in by Ghidra through a concept of a loader. And that loader, of which there may be many of, in this case there's a PE loader, is able to take information from the PE executable in this case, and it's able to digest that and turn it into constructs that are ready to go internally in the Ghidra application space. Now this is kind of assumptive at this point, but it seems to really lean heavily in that direction. As we keep digging, we'll learn more. And by the way, this can be a great way of diving into a program space even before you look at technical specifications if they happen to be available. Not all open source projects will have deep technical specifications, but to the extent they exist, sometimes they can be a little dated. Sometimes they might not read very well, or you might not prefer that way of looking at things versus something that's more hands-on. So in a sense, diving into a problem like this can act as a great specification, if you will. It's a great way of getting your hands on the actual architecture and looking at it firsthand and seeing those constructs at work. And neither avenue is better than the other. It really is context dependent. Sometimes a really good specification is best to start with and absorb the high level of a system. And then from that standpoint, you might look at the actual implementation or details. Sometimes the other way around is best. I find in the area of consumer software development and open source, where you're creating builds quite often and shipping quite often, new versions, new revisions, that the best approach is really to look at the actual source code, get your hands on stuff, start up a debugger, really see what's going on. That's what I find most of the time, and that's the world I grew up in. That's kind of the way I'm very familiar with. When I read a spec, sometimes I'll get glazy-eyed. It'll be time, to doze because specifications can put you to sleep. If they're very verbose, you're reading lots of detail that you really don't need firsthand. You want to see like a good overall map, and some specifications might provide that so they can be helpful as a starter. But at some point, you really want to get in and see those implementation details at work. Now, there are some software spaces where you really do want to take in those specifications. You really do need to be very methodical and go over things with a fine-tooth comb. And that's just something you'll have to figure out, given the entire situation that you're dealing with. And so with that in mind, I think we do have enough flexibility with this project to kind of be fast and loose, go in here, set some breakpoints, look around. And so that's what we're doing. And we see that it's actually yielding some good fruit. Okay, let's continue. So we see this PE loader is being called. There's a thing even down here. If we go further down, we can see there's like do load, right? Here's a thing called load. We can see there's loaded name. And if we look here, loaded name is console app. So we can see there's layers here that are kicking off. Oh, look down here. There's import utilities. And here's import single file. When you import single file, it ends up calling into PE loader here, all the way up here into this process memory blocks function. So process memory blocks here is actually doing something to process the memory blocks inside of the PE executable. And if you look, if your eye's quick here, you can see there's NT header and file header. So there's a bunch of things being loaded here. Let's see if we can find NT header here in the variables pane. And you can see here, there's some things here. There's file header, and it has a lot of information here. Here's like the machine 8664. That seems familiar. All right, let's search the web for PE executable. And if we go here, there should be a Microsoft, here's the PE format page. And this is the page that we looked at in one of the prior videos where we discussed the PE format. And let's search within this page for 8664. And you can see that 8664 is the image file machine, AMD 64 ID. So if we put this aside here and we go back over here to Eclipse, we can see this NT header includes 8664 for the machine. So it looks like this PE loader here within Ghidra is able to access the PE executable image header and other information. So even though that's not directly related to the problem we're troubleshooting, when we see familiar things, it can help us learn a little bit about what's going on in a particular area of the program. And since we already know about the PE executable format from the past videos, we can use that knowledge here to kind of see a little bit about what's going on here. And if you recall, we've talked about sections within the PE executable before, and this looks like it's getting some section headers right here, and it looks like it's processing sections here. And if you look down here, you can see that there is a for loop where it's looping through each section, or it will. Right now it's up here at create initialized block, and it's doing something with this initialized block here, which ultimately calls into this higher stack here where it creates the subblock. And in fact, you can see virtual size here is 1024. Let's go back up here to the top of the stack, and we can see that the value for the length of that record is 1024. So there's a correlation between what the PE loader here is doing and virtual size. And this virtual size is coming from the header block. Now, we're not going to focus on that particular value right now at this point. Let's actually go back up to what we were focused on. We see that a record is being added to the subblock table. It's not the record that we're looking for. So I'm just going to press F8 to go to the next breakpoint. I hit F8 and we hit the same breakpoint, so another block is being added to the subblock table. Now, this is a type 3, which is uninitialized, but it is 65536, and we're not looking for 65536. So we can see that that's being called in the same context, though, as the stack we previously saw. However, let's click down here and see kind of specifically where it's at. Oh, look, it's in a different location. I'm going to move this over a little bit, and I'm going to move this over a little bit so we get some more room here. And I'm going to scroll up. So we were last up here at create initialized block, but we have since entered into this for loop of iterating through sections. And we highlight I. We can see I is 0. So it's on the first iteration of this loop, and it's way down here. Let's click to go up here back to our breakpoint. And this is the place where we have type 3 and the value 65536. So let's hit F8 and to run the debugger again, and it looks like we are processing another uninitialized block of 65536. So we're not interested in that. We're looking for the one that's 1856. So I'm going to hit F8 again, and it looks like we've hit another kind of block, not uninitialized, and this one's 35840. Let's hit F8 a couple more times. I'm going to hit it one more time and another time and another time. Okay, so I've hit it 3 times, and it looks like we hit 1856. This is actually kind of good because it means I don't have to set a conditional breakpoint here. I just have to hit F8 a few times. Now, if I had hit F8 like 10 times and still didn't hit 1856, I would make the effort to right click on this breakpoint and choose properties, and I would have set up a conditional breakpoint here. But hitting F8 a few times is not a big deal, so we're going to go with that for now. If we have to keep coming back to this breakpoint, we may come back and set a conditional anyway. But for now, we have hit this breakpoint where we are creating or adding to the subBlockTable a new record, and it's of 3 uninitialized memory, and it has a length of 1856. And that looks like it's the block of interest to us. Let's go down here a few frames back to process memory blocks. Okay, we are down here in process memory blocks. Let's go scrolling up to kind of see specifically where we are located. And this was where we first were when that first block got created. And here's the top of the function. So there's the top of the function. It kind of comes in here and it does stuff like getting the header and things like that. It does some stuff here to do some calculations and creates this initialized block. And then it goes in and it iterates through these sections. And right now it is on section number 3 from the indexing perspective. So there's an array here called sections. And let's look over here in the variables window to see here's sections right here. And we can see there's quite a few sections. There's 10 sections here, and we are on section 3 here. So let's actually look at these sections. You can see the name here says .data. Now that's kind of interesting. Let's open up these other ones beforehand. There's our data and there's .text. And here's the 0 one, which is .text BSS. Well, this is quite interesting. If you remember from our prior video where we used dumpbin, we could actually dump the sections. Let's use the start menu and type in 2022, and that will show us the x64 native tools command prompt. And we also use this in one of the prior videos. Let's click to open up a Visual Studio command prompt. Let's change directory to the Ghidra deb directory, console app, x64, and debug. I'm going to start up PowerShell. Let's type in ls, and we can see there are the console apps. Now let's use dumpbin, and let's use it on the console app, and let's hit enter. Now you can see that dumpbin dumps the sections by default, so it's showing us all of these sections. And .data is the section that seems to have our uninitialized memory block. So the block in question that's getting created seems to be being created when this section is being processed in the PE executable. We can actually use the dumpbin command to dump the section specifically. So I'll type in .data and then console app, and we get some more information about the section. We see its name here. There's something called virtual size. There's virtual address. Oh goodness, something looks kind of familiar here. Remember earlier in the program, we had an offset that had D00, and then it had 1E0, and there was only 32 left. That's kind of interesting. Just something to keep in the back of our minds here, that there's a similarity here between what we saw earlier and what we're seeing now. Look at the raw size. The raw size is 200. Remember that we were at the end of a 200 hex byte area. That's 512 bytes. So 200 is 512 bytes in decimal. So remember that earlier we were at 1E0, which is 32 bytes before the end of that 512 byte block. That's kind of notable as well too. There might be a correlation here. Now, generally speaking, this raw data size value is the data which is contained within the binary. In this case, since it's the .data section, this would typically be initialized data, variables that are pre-initialized to some value, and that value is kept within the executable. It has to be kept within the executable because the executable, once loaded by the OS loader, needs to have pre-initialized variables initialized to the correct values. But we notice there's a thing called virtual size, which is larger than the raw size. So since the virtual size is larger than the raw size, it means there's some portion of this section, as it will be represented in memory once the program is loaded, that doesn't really have to be initialized by some value which is in the exe. It doesn't really need to bloat the executable because there is no special initializing value. Okay, let's go back to Eclipse. Okay, back here in Eclipse, let's actually look around here for a second and let's see what the section name here is. So the section name is, okay, so section name is here, and you can see that it's .data. So this is where section name gets assigned. It gets assigned by referencing the section itself using the index for the current section we're on in the loop variable here, I. So when I is 3, it will reference the section header. So you can see that sections is a section header array. And the third section header in this sections array will return a name.data. So I think what might be interesting is to place a breakpoint here at line 660. So what we can do here is let's beef up the breakpoint to break on section name.data, but only for console app.exe. Okay, well, we know that the program name is in the prog variable .name. But as we recall from earlier in the video here, let me actually delete these old expressions. As we recall from earlier in the video, if I type in just prog, right, that works fine, right? And we see here there is prog.name. But if I type in prog.name, it says errors during evaluation because it doesn't like me accessing the private member directly. Okay, let's go over here to the variables window and we're going to go to prog and then we're going to go down here to name. I'm going to right click on name and I'm going to select open field declaration. The name field is inside of domain object adapter. And let's actually just see if we can scroll down and find a get name, or we could actually just try get name on the object, on the prog object. So here's get name. Let's actually try that. So let's actually go back to, where's our stack location? Okay, let me double click to go back here to our breakpoint. You can also use the Alt and back arrow to go back to the breakpoint, but I find it's easier just to double click on the top of the stack here. If you don't have the stack here, make sure to click on the debug window here. And what I want to do is once we're back here, I want to go back to expressions and we can see that prog works. And as we said before, if you type in prog.name, that doesn't work because it's not a public variable and the debugger does not allow you to access something that's not publicly available, or that's the way it seems. If you type in prog.getName though, let's see if that works. Terrific, prog.getName returns the name. Okay, now that we know we can use getName, let's actually test the expression here in the expressions pane, and we're going to put in prog.name compare to console app.exe equals 0, and I'm going to stretch this out so it can be seen. And I'm going to press enter, and we see that it equals false right now. And that's correct because if we look at the name, it's equal to kernel 32 right now. In fact, as a quick test, I can actually go here and modify this to say kernel 32, even though that's not what we need for our breakpoint. It's okay to do it as a test right here. So we can type in kernel 32.dll, and we see it evaluates to true. So this will work in our expression. Let's actually move this window over here. I'm going to actually delete this right now so we just don't get confused by it. I'm going to right click on our conditional breakpoint and choose properties. And then with conditionals, I actually know that you have to actually put parens here. If you don't, you'll get some errors. So you have to put parentheses around the first conditional, then do and then put parentheses and put the second conditional. If you leave those extra parentheses out, it somehow, produces an error. It doesn't like that, so it needs those parentheses. So basically what this is going to do is it's going to break at this line number 660 when the section name is .data and the program name is console app.exe. Otherwise it will just skip over this breakpoint. So I'm going to click apply and close. Terrific. Now what I want to do is run through all of this to get to the point where I can delete and re-import the executable. So let me hit F8 until I get to that point where the debugger does not break anymore. So let me hit F8. Now it's hitting this uninitialized subblock breakpoint. I don't mind that. It's not going to stop here too often. So I'm just going to hit F8. I'm going to hit F8 again. I'm going to hit F8 again. And again. Again. Okay, I had to hit F8 like 5 or 6 times. And now the program is running. It's not at a breakpoint. Okay, let's go over to Ghidra and let's click OK. Let's delete the executable. Let's press I to re-import. Let's select the executable. Let's click OK. All right, let's go over to Ghidra. There's a breakpoint. This is on the uninitialized memory block. If we go down here to the loader, that's that first call, create uninitialized block there. This is that uninitialized block that is 65536. It's if we go down here to the PE loader, we can actually see that the section name here is .textbss, so it's not even our section. That's probably obvious by now, but I just wanted to, reiterate it so it was clear. So I'm going to press F8. And it looks like our conditional breakpoint hit. Let's double check what's the section name. So if we go down here and look for a section name, we can see it's .data. That's good. Now let's go here in prog and look at the name in prog. And the name in prog is console app. So it stopped here when the app was console app.exe, and the section that it's processing within console app.exe is .data. So if we go over here back to the command window where we use dumpbin and we look at the list of sections that we dumped in console app.exe, we can see that there's a section here .data, and we can also see when we dumped the details of .data that it had these details here: virtual size 940, raw size of 200. These values are in hexadecimal. So when this breakpoint gets hit here, it's processing this section right now in Ghidra at this breakpoint. Now if you'll look down here, you'll see it's going to get the raw data size from the section as well as the virtual size. Now we can take sections I and we can actually copy that over to expressions, and I'll paste it right into here, and I'm going to expand that, and we can actually just look at this directly. Now the value of I is currently 3, and we could add an expression for that here. So there's 3, and if we look at sections I, which is currently 3, we can see the name is .data. We expect that. The virtual size is 940, and by the way, that matches the detail here that shows virtual size is 940. Back over here at Eclipse, if we look at the size of the raw data, we can see it's 200. So we go back over here, we can see raw data is 200. So we can see a direct correlation between dumpbin's read of the PE executable for this particular .data section and what Ghidra reads for this section. Of course, they're going to be the same, and that correlation just helps us sanity check that we understand kind of what's going on here. Ghidra is reading the .data section for the console app.exe, and dumpbin is dumping that same section out for us here. Going back over here to Eclipse and going to the variables window, and I'm just clicking that just to have that available. I kind of keep the variables window active sometimes, and then go to the expression, pane as needed. But sometimes I, keep the expressions pane visible and then go to the variables window, or you can just rearrange the windows however you like. I'm just letting you know that so you don't think there's something I'm doing there that's really critical. You can arrange things however you wish to arrange them. So let's actually use F6 to step through here. So I'm going to step over this, and we can see it's actually getting information out from the header about this section. Now RWX looks familiar. Typically when you see RWX in relation to a PE header or something about memory, usually those are indicators of read, write, or executable. And we can see that the .data section has attributes that indicate it should be readable, it should be writable, but it should not be executable. We now are going to step over this, and we see that it is actually getting the raw data size, which is 512. It's going to get a pointer to the raw data, and it's going to get the virtual size, which is 940. Right here you can see 940. And it's now doing an if check here, and it's saying, well, if the raw data size is valid, meaning it's not 0 and there is a valid pointer, then it will go in here and process that. Let's actually trace into this. So I'm going to do F6, and here there's some notion of data size. So data size ends up being the raw size here, which is 200 hex or 512 bytes. And I'm going to do F6 to step through here. And now what it's going to do is create an initialized block for this particular area of memory. Now it looks like the size of that block is going to end up being 200 bytes. So for this first pass through, we're not going to trace into these functions. You can if you want to and you want to investigate those more. We're going to stick at a high level here and trace over these with F6. So I'm going to move this over a little bit and just create a little bit more room, and let's go and do F6. And let's actually go F6. And right here it says if the raw data size equals the virtual size, and we know that it doesn't. The virtual size is 940 and it's larger than the raw size, which is right here, and that's 200. Now we could actually do something here. We can go over to the calculator and we can go to hex here, and we can say 940, which is the virtual size, minus 200 equals 740. Now look at the decimal value for 740. It looks familiar, doesn't it? It's 1856. So it almost seems like that 1856 for that uninitialized block is anything that's over the size of the initialized portion. If we take that 940 hex bytes, which is the runtime size or the virtual size, and we subtract from that the initialized size, which is 200 hex bytes or 512 bytes in decimal. And that's the initialized stuff, which is kept within the binary, within the executable. And it needs to be there because that's going to be used to initialize that portion of the memory. So if we take that value of 200 hex and subtract it from the value, that runtime size of 940 hex, we end up with a difference there of 740 hex. That indicates that the virtual size, which is the runtime size, includes 740 hex bytes of uninitialized memory. And 740 bytes in hex is 1856 in decimal. If we go over to our notes in Visual Studio, we can see that 1856 was the number that we were looking at in the uninitialized memory block. So it seems like the PE executable console app.exe has a .data section that has a runtime size of 940 bytes, of which 200 hex bytes are initialized. And those 200 hex bytes are contained within the PE executable. The uninitialized bytes are not contained in the executable because they are uninitialized. Their initial value doesn't need to be retained in the binary. Let's go back over to Eclipse. So what this is saying here is if the raw size is equal to the runtime size or the virtual size, then continue. Otherwise, drop down here. This says if the raw size is greater than the virtual size, continue. And you can see a comment here, virtual size fully initialized. Neither of those cases apply to this situation. So then we drop down here. Is raw size less than 0? No, it is not. Okay, so we see that this case, and this case do not apply. Let's do F6 to confirm that. So I'm going to press F6, F6, F6. And we end up down here as we expected. Okay, we can see here it's going to subtract from the virtual size the raw size, which has already been processed. So let's actually see what happens. Virtual size right now is 940. So I'm going to press F6 to step over. And a virtual size now becomes 740, which is 1856. It's now going to take the start address for this section. So let's look at that start address. We can see the start address is that 14001D000. And that's the address of that initialized block. But since that was just processed, it's now going to do an address calculation here by adding that part that has already been processed. So it's going to add 200 hex bytes to the address. So let's press F6 to process that, and we look at the address, and you can see the address has now changed to have an offset of D200 at the end here. Now it drops down here and it says, well, is the virtual size 0? It is not 0. It's equal to 1856 decimal or 740 hex bytes. Let's hit F6 and it drops down into here. It's now going to perform a calculation to determine the data size, and the data size ends up being 740. So let's find data size in here. Here's data size, and that just ends up being pretty much what virtual size was after the adjustment, which is 1856 or 740 bytes. And this if statement is just saying if data size is greater than 0, then go ahead and create an uninitialized memory block. And this is where the uninitialized block gets created. Let's actually do F6, and sure enough, it's about to create this. Quick recap is that we experienced that exception and we placed some breakpoints and did some tracing, and we got to a point of having a breakpoint in the uninitialized sub memory block. From all of that, we discovered the characteristics of the memory block we were interested in, that it had a type of 3, meaning it was uninitialized, and that it had a length of 1856. We then found the place where it creates that record and adds it to the table. That led us to this stack here where we're looking at the PE executable sections being processed. The memory blocks get created as Ghidra is processing the PE executable sections. And here we are where it was processing the data section, and as part of processing the data section, it created 2 blocks. One block was for the 200 bytes of initialized memory. The other block was for the uninitialized portion of the data section. If we go back to the command line here where dumpbin output exists, another way of saying it is it created 2 internal representations that represent the .data section. The first one is an instance of the initialized memory block, and it has a size of 200. The other one is the uninitialized submemory block, which has a size of 940 minus 200, which is 740, or that value 1856 that we've been looking at for a while. Let's go back over here to Eclipse. So we can actually trace into this. I'm going to hit F5 to trace into this, and we end up in this function create uninitialized block. I'm going to step over this function with F6. This gets a thing called memory from the program, and memory happens to be an instance of MemoryMapDB. So if we look here at memory, we can see it's a MemoryMapDB. Here's where it creates the block. I'm going to actually press F5 to step into that. When we step into that, it calls create uninitialized block, and it's going to go in here, and I'm going to step over these with F6. So F6, 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 F6. Now I'm skipping over things that are doing checks and doing things that are relatively unimportant to our focus. We want to get to the point where it's creating the block down there. So I'm going to press F6 again, and here we are at create block. So I'm going to press F5, 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 and we step into create block. And this is going to do some checks here. I'm going to press F6, 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 and it gets down to the bottom here where it's going to call create uninitialized block. And it's doing that because none of these other cases applied. I'm going to press F5, and now it's going to go and create this subblock array, and it's going to create a memory block record. That's a database record. We can actually trace into that. I'm going to do F5, and now I'm going to do F6, 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 F6. This is basically just setting all the columns for the record to the values that were supplied to the method. I'm going to press F6. I'm going to press F6 again, F6, and here is where it creates the subblock record, and it's going to add that subblock record to subblocks. And subblocks is going to become part of this memory block DB. Let's actually go and see what happens in create subblock record. So I'm going to press F5, and it's creating another record. Now this is a record for a subblock, which is different than a record for a block being sort of the parent of a subblock. In our particular case, since there happens to be one subblock to the block, it's almost like they're both sort of synonymous. They are different things to Ghidra, and we know there's likely a reason why Ghidra has a concept of a block versus a subblock, and there's likely some cases where it can have multiple subblocks to a given block. But in our case, we know that the blocks we've been looking at each have one subblock. But we don't make the assumption that that's a rule of thumb everywhere. We just know it happens to be that way in our situation that we're looking at here. So we press F6 and we trace through all these. These are just setting up the columns for the new subblock record. And this is where our breakpoint is. If you look here, this is where we have a breakpoint right here. And this is the breakpoint that adds to the subblock table. And it's adding a brand new record for the subblock that it's creating. And if you look here, you can see the type is 3 and the length is 1856. So this stack actually here, if we go back to PE Loader, you can see that this section here, you can see that this is the cause for that problematic block getting created. So let's go back up here and hit F6. And I'm just going to keep hitting F6 here until we return back out and bubble up to the calling function here in the PE Loader. So I'm just going to go past all of these. And we're going to go back here to where it returns the block, and we're back here. So we see that Ghidra is processing this executable. It's going through the sections. The data section for the console app.exe is 940 bytes at runtime. That's the virtual size. There are 200 bytes of those 940 bytes, and this is hex, which are initialized. Those initialized bytes are in the binary itself. There's 740 uninitialized bytes that are part of the data section. There is no data in the binary for those bytes. Therefore, the binary only has 200 bytes of the entire 940 byte section. It ends up creating two different internal representations for the entire .data section. One is a subblock that is initialized, and the other is a subblock that is uninitialized. The initialized subblock is 200 hex bytes, which is 512 decimal, and the uninitialized portion is an uninitialized submemory block, which in hex is 740 bytes or 1856 in decimal. So with all of that knowledge, let's actually go back to the original problem and look at some details there. Because the one thing that's puzzling is Ghidra is trying to read some data, and it's only able to read 32 bytes. It's not able to read the rest that it was trying to read, which I think was 152 bytes. Let's go back there. So in order to get back to that context where the problem is occurring, we need to import both of the binaries and run that automatic version tracking. So let's press F8 here to go past this breakpoint. And let's press F8 to go past these uninitialized submemory block constructors. Okay, so that's one binary that's been imported. I'm going to click OK. I'm going to press I, and I'm going to select console app 2 and import and OK. And it's stopping at this uninitialized submemory block. I actually don't think we need that breakpoint after all at this point. We might enable it later. So I'm just going to merely right click on it and disable it, but we'll keep it there. That way we can always double click to come back here from the breakpoints tab. We can actually just double click and come back here and re-enable it. So with the breakpoint disabled, I'm going to press F8. I'm going to go back to Ghidra. It's actually loading everything up. It's finished. Okay, both executables are loaded. Now I want to double click on the first one to load it in. Okay, it wants to know if I want to analyze this. And even though I know the symbol path is already set up, I'm going to say no and just double check to make sure the symbol config is correct. And the symbol config that we had before is still there. That's what I would expect. I'm going to click OK. I'm going to press the A key to analyze. I'm going to click Analyze. And I'm going to keep an eye here on the lower corner. We can see when it's finished. And it might pop up a box if there's any warnings. Okay, it's finished. I'm going to click OK. Okay, I'm going to click the X up here and then save. I'm going to do the same thing with console app 2, except this time when I'm prompted to analyze, I'm just going to say yes because we know the symbol path is still set up correctly. And I'm going to wait for auto analysis to finish on this. I'm going to click OK. I'm going to close the window, choose to save. I'm going to highlight both executables. I'm going to right click, open with version tracking. This looks correct. We have the original one and then the one where I put the number 2. I'm going to click next, precondition checks, next, finish. And we have, this is the source window, and there should be another one in here. There is the destination one, source, destination, and here's the version tracking window. Our breakpoint is already set on that data.get.bytes call, so let's just click automatic version tracking. Let's go over to Eclipse. Here we are at Eclipse, and the breakpoint is already hit because you can see that this button is enabled, the continue button, and you can also see the highlighted line here. Now, the goal of coming back here is to simply expand AData and look at this a little more closely. So as you recall, AData has a thing in here which is base data type, and this indicates the type, which is a structure. And it looks like it has the name of the structure, and the structure is exception record. The struct length is 152. Now, I happen to be familiar with exception record, and if you've done a bit of Windows programming, you probably are familiar with exception record as well. There's a couple of things we could do here that might be interesting. I'm just going to pick one of them. You could do these in either order. So one thing I'm going to do is start up Visual Studio 2022 here, and I'm going to click to open up the console app project. And what I want to do here is I want to add the Windows header here. And I'm just using this project actually for utilitarian purposes. So I'm adding the Windows header. And then down here, I'm going to add exception record. And I'm just doing that so I can put the cursor on it and press F12 to go to the declaration. And here is the declaration right here. So we can see that this thing has a D word, a D word. Here is a pointer value, a D word, and then ulong pointer is the size of a pointer. So effectively, this is an array of integers that are the size of a pointer, or that have the same magnitude as a pointer. We can see that exception maximum parameters is 15. So this is 15 integers that are the size of a pointer. And since we're talking about x64, we're talking about 8 bytes per pointer. So we could actually write a program to do size of, but actually let's just calculate this in the calculator. So I'm going to go to the calculator and I'm going to highlight decimal. So I'm going to add up the size of these. So for x64, D words are 4 bytes. So what we have here is 4, 4, which is 8. And then this pointer here is 8 bytes. This pointer is 8 bytes. This is 4 bytes. And each of these is 8 bytes. So we have 8 times 15. So let's do 8 times 15. And then we have plus 8 plus 8 plus 8 and plus 4, which is 148 in decimal or 94 in hex. Now you recall in the past video where we talked about how a hex value has 0 in the last digit if it's 16 byte aligned. Well, you can also use a little trick to determine if a hex value represents something which is 8-byte aligned. So 8-byte aligned would have a final hex digit that would either be 0 or 8. This particular hex value 94 ends with a 4, and a 4 is not 0 and it's not 8. So this size is not 8-byte aligned. It doesn't fill up space to an 8-byte boundary. In order for it to fill up space to an 8-byte boundary, we would have to add 4 to that value. So let's add 4 to the value 148. So 148 plus 4 brings us to 152. Now if we go back over to Eclipse, if you look here, the struct length is 152. So let's go back over to Visual Studio. You might ask why we added that 4. Well, this is compiled or built with 8-byte alignment. Now you can change the alignment, but by default, this is going to be 8-byte aligned. Because this structure doesn't have an equal number of 8-byte items, it has an extra 4-byte item. So if you look, these two D words are each 4 bytes, so that's 8 bytes. This pointer is 8 bytes. All of these pointers are 8 bytes, and this pointer is 8 bytes. You have this thing standing out. Now, it's not really this particular field which is standing out. I'm just picking it because it's a 4-byte field. I mean, I could have said this D word and this D word are 8 bytes. This is 8 bytes, this is 8 bytes, all of these are 8 bytes. So the leftover here is this one. I'm just trying to say we have an extra 4 bytes here. We don't have an equal number of 8 bytes in there. Therefore, the structure doesn't naturally align on an 8-byte boundary. So the compiler is going to pad at the end of the structure enough bytes to make it 8-byte aligned. It really is doing that so that the next variable that comes after that structure will start on an 8-byte boundary. If it didn't do that, the next variable might start, earlier than that, right after the structure. But the compiler is going to build things in a way where it's going to fill out the structure so it fits perfectly into an 8-byte aligned area, meaning that 1 byte past the end of the structure will be 8-byte aligned. And that's why you see over here this 152. It's because the compiler actually creates a 152-byte area for the exception record, even though it doesn't need those last 4 bytes. And Ghidra is just simply seeing that information. Okay, so let's actually do something else here. Let's go back over to Visual Studio and let's go to the console app. Okay, so I'm going to delete this exception record thing here and I'm going to delete windows.h. We now have the original console app here. I'm going to right click on the console app here and choose properties. So I'm going to expand linker and I'm going to go to the debugging section here. In the debugging section, there's a thing called map file, generate map file. I'm going to double click that to change it to yes. I'm then going to click OK. I'm now going to build the executable, and there it goes. It's being built. And now what I'm going to do is I'm going to open the folder, and I'm going to go to the build directory, and we can see a map file has been created. I'm going to right click on that map file and choose VS Code, and VS Code is going to open up and it's going to show us this map file. Now, what I want to do is scroll down here and let's look for .data, and you can see here is the .data section, and you can see the .data section is section 4 in an area that's indicated with this sort of indication of 4. What's interesting is you can also see BSS is in 4 as well, but BSS does not appear in the section output. So if we go here, we don't see any BSS. Well, we see text BSS, but we don't see .bss. Going back over to the map, this is .bss, and it comes right after the .data section. What I want to do now is I actually want to select 004 and colon and do Control F. That's going to search for 004 colon. Let's actually hit F3 to find the instances of that one by one. So here we're at the first instance, and we do it again and again, and now we're down to a whole bunch of stuff which is in that section. Let's actually go to the bottom here and click, and then hit F3. That takes us to still more stuff down here. Let's go below all this and hit F3 again. And now we wrapped around back to the top. So let's hit F3 again a couple times, and let's look at this really quickly. So there's a bunch of values here that seem to reside in this section. So let's really quickly go back to Eclipse here, and let's actually step into the DataDB.getBytes, and let's go to that place here. I'm going to hit F6 now, go down here, F5, 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 Let's go down here, and this is where it reads the first block. And let's look at this first block. That first block is at D1E0. Okay, so let's actually go up here and look at A data. So remember, A data is a base data type, which is a structure, and it is an exception record. So let's go back here to the top frame, and you can see here that there is an adder, and this address ends in 1E0. So remember, 140001D000 is the start of the .data section. This address offset is 1E0 into the .data section, meaning it starts at the last 32 bytes of that initial 256 bytes. Let's map this out really quickly over here in VS Code. So let me go to VS Code. I'm going to say new file just for a scratch file here. So let me actually get that address here. I wanted the hex address here. Will this give me the hex address? Oh, terrific. So the start of the data section is actually 000. Let's actually verify that. I think that's in the output here. So if we go to the output, yeah, right here you can see it has 1400001D00. So let's copy that. Let's paste this in here. And actually, if I just highlight this and do Control F, you can see it matches exactly to this. So we don't really need this. I just wanted to show you that they match. And I copy pasted this only to just get this value so I could replace the last three hex digits with 0. So .data start. In fact, let's do it this way. .data start. So A.data.getBytes is beginning its read here at 1E0. So this is A.data.getBytes start read location. So as you recall, it is able to read 32 bytes from this initial block. So if I actually copy paste this and put this here and put 200 here, this is .data start of uninitialized, .data start of uninitialized section of uninitialized portion of section. 1 byte past the end of the initialized section. So I'm going to click save because we might want to save these as our notes, and I'm going to put these in Ghidra dev docs, and we'll call this .data information. .data info. So you will notice that between this start read location and let me just put like textual arrows here. Forgive my informality, but I'm just going to put these. I'm going to say 32 bytes available for reading here. So basically what Ghidra does is it loops through those blocks and it tries to read the 152 bytes from the first block. But it can only get 32 bytes because that's the initialized block and it has 32 available. It then tries to fulfill the remaining read of bytes. So if we say 152 minus 32, we would say that's 120. So there's 120 bytes remaining to be read. And so it's trying to read, unable to read remaining 120 bytes from this uninit portion of the .data section. Do you kind of see the picture that's kind of developing here? So let's go back to Eclipse. And we see this is the first block and it's located at that address offset that ends at 1E0. So this one's going to be successful because it's using this block here, which has a subblock that is of initialized memory. It's called FileBytesSubMemoryBlock, and it represents those bytes that are available within the binary. So this portion of the read will be successful, as we know. So I'm going to just do F6, F6, F6. You can actually see that last read read 32 bytes, as we saw before. And let's do F6, F6. And we're doing F6 here, and we can see that numRead is 32. And let's actually see what it's going to do here. It's going to say size minus numRead. So it's actually doing the math here. 152 minus what it already read, and that's going to be the 120, which it's going to try to read. But it's not even going to get there. Let me actually step through here to get that block. And the reason why is, as we know, this block has a subblock block, which is uninitialized submemory block. And we know that we get these two blocks. We know the first block comes from the initial 200 bytes of that section, which is included in the binary. For any bytes in the .data section, which are not included in the binary, Ghidra goes and creates an uninitialized memory section. And the way Ghidra is set up, you cannot read successfully from an uninitialized memory section, which is what causes Ghidra to fail here, because it can't read any bytes from there. It doesn't get anything back from that. And the reason why is an uninitialized block is going to return false for is initialized. So this is going to leave only having read 32 bytes. And as we know, the caller is going to check that here. And it's going to say if 32 is not equal to this 152 value, which it isn't, it's going to throw the memory access exception. So if we go back over to the map file, let's go to this map file. Let's actually try to see what is located at that 1E0 place within this section 4 here, this 4 colon segment or section. So here in the map file, if I do Control F and search for .data, we can see .data ends up having section number 4. And section number 4 starts at 0 and ends at 1B0. We also notice that .bss, which is another section, is considered to be section 4. It seems as though the compiler and linker end up ultimately putting .bss and .data into one section, which is .data. And so both of these are considered to be section number 4 in this map file. Let's actually highlight 0004 colon, and I'm going to do Control F, and we're going to search for uses of this section number within this file. So I'm going to press F3, F3, F3. So here's a bunch of stuff that appears in that section. Let's actually click past that, and let's press F3, and we find another bunch of stuff. And now let's click past that and press F3 again, and that wraps around to the beginning. So we know there's two kind of areas that show stuff that is in section 4. Let's hit F3 to get to the first group of items, and then let's scroll up with the scroll bar to the top here, and you can see this section has publics by value. Now let's hit F3 to go back to this first group. Let's click past the group and hit F3 again, and we go to the second group. Grab the scroll bar and go to the top up here, and you can see that these are static symbols. All right, let's actually go to the top here, press F3, F3 again, and F3 again, and that brings us to the first group of items. Now, if you look at the first group of items, you can see here that there is something at 1B0, right? And this is at 1B0, and it's a thing called options storage, and it's located here. And this looks like something from the runtime library given that. So what we could do is we could actually take this, copy that, and we can go over here to Visual Studio, and we can do Control, Shift, and F and paste that in here, and then make sure that we choose to search in Visual Studio, all Visual Studio directories. Let's just do that. And let's click Find All. Okay, it found that. Let's actually double click here and look at this. So if you look here, you can see that here is option storage. Option storage is 8 bytes long because it's an int 64. It's a static variable. Let's go back over and look at that. So here's option storage. And if that were 8 bytes, it would go from 1B8 to 1BF, where 1C0 would be the next variable. But we don't see 1C0 here. It just jumps to 868. So let's click down here and press F3 to jump down to this second group in the static symbols area. Okay, we see something at 1B0, and then we see something at 1C8. Okay, so we see some other items here. Now, look at this. If we go to 1E0, that's the beginning where our DataDB.getBytes, the one that fails, that's the beginning of where that exception record resides. Let's clarify this. Let's go over here to the Eclipse workspace. Let's actually double click here to where our AData.getBytes is. It's right here. This is the AData.getBytes. This AData.getBytes is the one that fails. It fails because that second block is uninitialized and can't satisfy the rest of the 152 bytes that are needed. Really the remaining bytes, which is 120 bytes of the 152. The initial 32 bytes is satisfied from that initial read. That initial read takes place at the initial address. Now, if we go and look at this AData and we look at its address, and we've seen this already before, but let's just look at it. Look at the address. It's 14001D1E0. So let's go over here to the map file. At 1E0 in the map file is GS exception record. Okay, let's grab a GS exception record. Let's copy that to the clipboard. Let's go over to Visual Studio. Let's Control-Shift-F, paste. All Visual C++ directories should already be selected. If not, select it. Click Find All. And you can see right here that GS exception record is an exception record. And we already know that exception record is that thing that's 152 bytes in length. Let's go back over to Eclipse. If we go to Eclipse, we can see that A data, which is right here, has this address offset, 1E0. And if we go down, we see that it has a length here of 152. And 152 is that exception record padded with the extra 4 bytes. If you do a size of exception record, it's going to come out to 152. In fact, we could test that really quickly. Let's go over to the console app. Let's go here. I'll just do a quick and dirty test here. We're going to say include, okay, come on. Windows.h, please. Okay. I'm going to just do something quick here. We're going to just do that, size of, exception record, and that's fine. I'm just going to run that really quick. Control F5 is what I did just to run it. I'm not going to debug it, and it comes out to 152. So we can close that window, and I'm going to undo this so we have our original little test app here. Okay, let's go back over to the map file. At the map file here, we notice that this exception record, now this exception record is, this is 152 bytes long in length, right? The size of it, right? So if this is 152 bytes, it's going to go from 1E0 to like, 2 something. That means that the start of this exception record is partly in the initialized portion that is within the EXE. There is another portion of this exception record which exists in the virtual area that is not included in the space allocated for initialized data in the executable. Therefore, this GS exception record spans from the initialized portion of the .data section to the uninitialized portion of the .data section. Now, this is not a problem for the executable because the OS is just simply going to load in the executable, it'll set up the memory, and once the memory is set up and initialized and all that, the full exception record will be fully accessible to the program when it's running. But Ghidra is kind of breaking the data section into 2 portions. One is an initialized section and one is an uninitialized section. And because the structure spans both of those, when Ghidra tries to process that one structure, the portion that's processing the structure expects that the structure is going to be fully accessible and readable in entirety. If the beginning portion begins in an initialized area, Ghidra is assuming the whole thing will be available in an initialized area. But that's not actually the case here. And there is likely some history and some background to this. Okay, so now that we have more of an idea of what's going on here, what the problem is, let's actually make a small assembly program that will really accentuate what's going on here to us. We're going to use the skills that we have touched on in the recent videos that touch on assembly language, and you don't have to have all those concepts under your belt in order to follow along here. I will touch on the pertinent items, as we work through it, but if you want to understand more of the fine details, you might want to catch one of those earlier videos. I will link them in the description below. Okay, so the first thing we're going to do is I'm going to click stop here in Eclipse to shut down the debugger, and then I'm going to actually exit Eclipse. Okay, with the debugger stopped with Eclipse, let's go over to the command line into our Ghidra dev directory, and I'm going to make a subfolder under Ghidra dev called asem, so makedir.\asem. And then I'm going to go into that folder, and then I'm going to create a new assembly file, init uninit datasection.asem. And we're going to start off with this boilerplate code here. This is similar to the code that you might have seen in the past videos. We have a couple new things here that we're going to touch on. The next thing that I want to do is go to the start menu and type 2022, and then I want to click on x64 native tools command prompt for VS22. That's going to open up the VS22 tools command prompt. I then want to type in ML64 and /?. Make sure that we have access to ML64, which is the MASM 64 assembler. Okay, I'm then going to type in cd /Ghidra dev and then our asem folder, and I'm going to start up PowerShell. And I'm clearing the terminal window there. I'm going to save our assembly file here, and we should see it here. Yes, we do. Good. Okay, now let's grab this command line here, and let's pop this in here and make sure we can assemble this, and it looks like it assembles just fine. Okay, so let's do a quick rundown on this. Let's start down here in the main procedure. Just we'll kind of start here and then work our way up. So let's, for a second, let me just highlight this code here, and let me just for a quick second remove this, and I'm just going to put ... For this particular example, we actually don't need this prologue and epilogue code, but I just included it since we used it in the past examples from the prior video. This is allocating shadow space, and this is deallocating shadow space. And this is setting our return code to 0, and this is returning back to the user mode kernel module, kernel 32. Kernel 32 will end this thread and end the process. And we'll set the process's exit code to 0 for anything that happens to be monitoring for that exit code, including the process that spawned the executable, which might be the shell in this case. So that's kind of boilerplate code there. I'm going to actually undo the code that I removed. This is just code which is showing access to two memory variables that we are defining here. .data is the data section, and .data ? Is the uninitialized data section, which is .bss. What we're doing is we're creating the initialized data section first. We're creating a single variable in that section, which is initialized to a value of 200 bytes, having the value of 5. We're then following the initialized data section with .data ? Which is the uninitialized data section. And we're putting a single variable in there of a structure, myStruct, which is a total of 152 bytes, and it's uninitialized. This means that the assembler and the linker are under no obligation to initialize the space occupied by my uninit var. Okay, this one, my init var, is db, which is defined byte, and it has 200 dup5, which is duplicate. So there's 200 bytes, which means do db 200 times, each time with the number 5. So that's going to be 200 bytes, each having the value of 5. And you can refer to this operator as dup, dup, or duplicate. Now, this variable is going to go into the data section of the executable. And since it is initialized data, it has to reside in the executable. By residing in the executable, the loader can load the program, including this initialized data, and can initialize the variables or this memory space with the number 5 that we instructed it to initialize it with. My uninit var is short for my uninitialized variable, and it is going to be a myStruct with less than greater than. So myStruct less than greater than, that means there's no parameters that are being specified here. So it's just myStruct. This is kind of the way you specify a structure. We're going to look at it in more detail after we build it. The way that the structure is defined, we specify the alignment. So it's going to be 16-byte alignment. We give it a name, and we follow the name with struct. Now this is kind of similar to proc, right? Here's the name of the proc. We put proc after. So you can think of this as kind of like languages where you say function and then the name of the function. In this case with assembly, you actually say what the name of the thing is and then what the thing is. And so with a struct, you have myStruct, which is the name that we're giving it. We can choose any name we want. Then we use the keyword struct here. That tells the assembler we're defining a structure. And we're saying to the assembler, when you do use this structure, ensure 16-byte alignment. The structure is going to have one field, and the field is going to be a DB 152 dup ? Now what this means is there's going to be one field of 152 bytes. We don't care what the byte values are, so they can be uninitialized. That's what the question mark is doing. And when you want to use the structure, you give the variable a name, and then you put like one or more spaces, and then you put the name of the structure. The less than and the greater than act as brackets, and when the brackets are empty, it means there's no initializers for the structure. We just wanted to create space for that structure. So basically the var, my uninit var, is going to be allocated 152 bytes starting at the address given to this label, and that 152 bytes will be for field 1. And down here in the body of the main function, you can see that we're loading the offset, which is really the address in this case, of my init var into the RAX register. And then we're loading that address with the byte AA. That means it will store AA into my init var. The first byte of my init var will get the value AA. The next line is going to load the offset, or the address in this case, of my uninit var into RAX. RAX in this case will therefore point to the first byte of field for my uninit var. We then follow that line with move byte pointer RAX, comma, BBH. This is going to load the value BBH into the memory location pointed to by the RAX register. This line, in effect, is going to load the first byte of field of the myUninit struct variable with the byte BB. These are being done just to simply reference those memory locations so that they look like they're being used in case there are any link time optimizations, such as removal of areas that don't look like they're used and so forth. We want everything to be kept intact and left in place. And while we could enable some linker switches to avoid optimization, it's just simpler to show how to access these variables here and how to load some data into the variables. And plus it might be instructive as well just to see that. So that's really why all of this stuff is here. It doesn't really provide any functionality for us in our goals with this program. Our goal with this program is to create an initialized variable of 200 bytes long, and then to follow the initialized data section with a single variable of a structure, myStruct, which is a total of 152 bytes, and it's uninitialized. Okay, so we're able to build the program successfully as we've seen. So after we build, if we do ls, we can see that there's one exe there. Let's take that exe and let's actually copy that exe to another copy here that has the number 2. This is similar to what we did with the console applications. And there we go. We got this and we've got this. Okay, let's go over to Eclipse here and let's actually click to run this thing in the debugger. I'm going to choose Ghidra. I'm going to select all of our settings here from before. I'm going to press delete and click OK. I'm now going to press the I key to import a binary, and I'm going to use the up arrow to go to the top Ghidra dev folder. I'm going to double click to go into a SEM, and I'm going to choose the first exe, and I'm going to click select. I'm going to accept the defaults, click OK, open this up into a code browser. And I'm going to say, no, we don't want to analyze it. I'm going to go edit symbol server config. And what we want to do is add a directory here for the location of the symbol file for this assembly language program. I'm going to click the ellipsis. I'm going to type Ghidra dev asem. I'm going to choose OK there and OK. And there it is there. I'm going to choose OK. I'm then going to do a test here by using load PDB. Now the PDB will be loaded when we do the analysis, but this is a good way to visually see there's a green checkbox here and the PDB is accessible. I'm going to choose load and I'm going to choose A for analysis and I'm going to choose analyze. Analysis found the symbol main. Would you like to go to that symbol? I'll say yes. And here we are at main. Now, one quick thing we can do before we close this is we can actually go over here to the data section and we can see my init var is right there. And if we go down a little bit further here, we can see further down at 1EF, really at 1F0, the .bss section starts, and there is my uninit var. An interesting thing, and this is a clue to what we're leading up to here, is you can see that my uninit var actually begins at 1F0. This is at the tail end of the data that is included in the executable. And notice how it's initialized with 0. If I right click on here to expand all data, you can see that the initialized zeros go all the way to 1FF. That's the end of that initial 512 byte range, which is initialized data that is included in the exe. So what we see here is we have my uninit var, and it's 152 bytes long, similar to the way the exception record was 152 bytes long. And it begins within the initialized data section, similar to the way the exception record, was laid out in the console app. Yet it has an uninitialized section as well. It spans into that section. So our goal here with this small assembly language program is to kind of mimic the layout that occurs in the console app, where you have a single structure, which is the size of the exception record. I didn't use the exception record because we don't really need the specifics of that record. We just needed a structure of that size. And frankly, as you'll see soon when we get past this particular part of the demo, you only really need a structure that will span this area going from the initialized section to the uninitialized section. I'm going to do Alt and back and back and back to get to main. In main here, you can see that we set up our, RSP minus 28, and here are the instructions we specified, and here's our exit code. Not really a big deal. We don't really have to spend much time on it, just FYI. I'm going to click X here to close this window, and I'm going to choose to save. I'm going to press I to import, and I'm going to import the second copy. I'm going to say OK. I'm going to say OK. I'm going to double click to open it up. And when this prompts me for auto analysis, I'm going to say yes. Because we've already set up the symbol path, I don't need to do that again. I'm going to click Analyze, and it looks like it's already done analyzing. So I'm going to click Close and Save. Now I'm going to highlight both of these, right click, Open With, Version Tracking. Okay, it's not a big deal, but we want the first one to be here first and the one with 2 to be second, just for consistency's sake. I'm then going to click Next, and I'm going to run the precondition checks. We ignore these caution symbols. We click Next, click Finish. It's going to open up version tracking and the 2 code browsers. Here's the source browser. Here's the destination. We're now going to click the version tracking window, and I'm going to click to do the auto analysis. Now keep in mind, we're running under the Eclipse debugger. We have our breakpoint set. Let's run the automatic version tracking, and it's going to run. Let's go over to Eclipse to see what's going on. It looks like we've hit a breakpoint. And as you notice, we went right to the error. And that's because this breakpoint here is conditional, and the condition is not going to match for our assembly language programs, because those programs likely have a different offset than the one for the console app. We can examine that because we're at this breakpoint where the exception is being thrown. And actually, the exception got caught here. That's the memory access exception. And then this catch handler is actually rethrowing the exception by wrapping this exception into a new exception that is more applicable to the higher levels, which will receive all of this error data. Rethrowing exceptions and wrapping exceptions is a topic for exception handling in Java. You can read more about that online. I'm just covering it very briefly. And let's open up A-data as we did before. So here's A-data, and we can see it is a structure. We can actually see that its length is 152. That's similar to exception record. The name is my struct. Let's look at its address. Here's the address. Now the offset of the exception record was 1E0. It's off by 16 bytes, which is not a big deal for showing an example here. It's at 1F0, which is 16 bytes into the tail end of that initialized data section, and then the rest of it continues in that uninitialized data section after 200. So all we have to do here is single click to go into edit mode. I'm going to press Control-C to copy that value to the clipboard. I'm going to go to our breakpoint, right click, breakpoint properties. I'm going to click here to replace that offset with the new offset, and I'll tail end it here, suffix it with an L for long. I'm going to click apply and close. And now our breakpoint should work, so we can actually try this again. So let's hit F8. We hit F8 and it looks like the debugger is running. Let's go back over to Ghidra. Here's the exception error. Let's just click OK on that and run the version tracking again. Go over here, and it looks like our breakpoint was hit here. So we didn't stop here, but instead we stopped here before there was a problem. Now what we can do is we can do F5, trace in. Let's go F6 to go down to this call. Let's do F5, 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 F5. Now we're going to go F6 down here. We get the first block. Let's see what the address is. The adder is an offset which ends in 1F0. Let's open up block, and we can see block has a subblock, and the subblock is a FileBytesSubMemoryBlock. We're now going to F6 to step down here, and we're going to do another F6. And when we do this F6, we can look at last read. Now remember, before we did a read from 1E0, and that gave us 32 bytes to read out of that first initialized block there. In this case, we're reading from 1F0, which is only 16 bytes before the end of the initialized section. That's why we see in this case it was only able to read 16 bytes. And so the first read was successful. It's trying to read a total of size bytes, which is 152. It was only able to read 16 bytes because that's all that was available starting from 1F0 in that first block. Now I'm going to press F6 to go to the second iteration. You can actually see that num red here is 16. and size is 152. So of course numRed being 16 is less than 152, meaning we have more bytes that we need to read in order to satisfy the caller's request. Here's the address, and you can see the address is starting at 1F0, but now we're going to increment the address by the number of bytes that we just read successfully, which is 16. So we're going to increase the address by 16. Let's do F6, and we can see now we're at address 200. And when I say quickly and briefly like address 200, what I mean is the long address here that we're very familiar with, but the one that ends with the offset 200. And this 140004200, that address is the beginning of the uninitialized section. So our structure, myStruct, begins at the very end of the initialized data section, but it continues. The rest of its allocation is in the uninitialized section. And in terms of loading the program in memory and running it, there's no problem with that. If the beginning of the structure just happens to be initialized, okay, big deal. The program's not expecting any particular initialization, so it doesn't really matter whether it's initialized or not. It being specified as not initialized is simply a hint to the build tools. The values that start out in this variable that I'm allocating and declaring here don't really matter to me at the beginning of the program. I don't want them pre-initialized. That's different than initialized variables, where the developer has some expectation that the variables are going to start off with some particular value. And in that case, a developer will set some kind of variable to some initial value, and the build tools will include that in the initialized data for the program. All right, so I'm going to continue forward here, and we got the next block, and let's look at that next block really quickly. We open this up, and we can see that this block here has a start address here of 140004200. And if we look at the subblock, we can see it's an uninitialized submemory block. And because it's an uninitialized submemory block, we already know what's going to happen here. I'm going to do F6. Now I'm going to do F5, F5, F6, F6, F5. We see that isInitialized returns false, so we'll step out. I'm going to do F5 into isMapped, and isMapped is actually going to return false as well. And because both of those return false, it's not able to read anything. It's going to exit this function and return less bytes to the caller than what the caller had requested. That seems to be happening here. I'm going to do F6, F6. And here we are at the caller, and the caller doesn't like the length here because it doesn't match what it requested, and it's going to throw a memory access exception. Let's pause here really quickly, and what I want to do is I want to go over to the command line where and I want to recall the assembly command line here, and what I want to do is I want to add /map to the linker switches here. So everything following the /link switch is a linker switch, and we're just adding /map, and it's going to create a map file for us. So I'm going to hit enter and do ls, and we can see here's our map file. Let's run VS Code to load that map file. The map file gets loaded. Let's actually look for the data section. So this is showing us here that the data section is the third section here. Let's actually do Control F to find things which are in the third section. Oh, we also see that the BSS section is the third section as well. So both initialized and uninitialized data happen to be in the .data section. Here it makes it look like there's two different sections, but in the binary itself, the .data section actually ends up including both of those sections. So I'm going to press F3, and we end up going down here, and we see the two variables that we declared. The myInitVar is in the initialized data section, and it begins at offset 000. The myUninitVar is also in the third section. We know that this is in the uninitialized data section because we wrote the program and we know the source code. But the linker ended up putting it starting at the tail end of the initialized data. In this particular binary, the initialized data takes up 200 hex bytes or 512 bytes, but that full 512 bytes is not needed for all the actual initialized data. So the linker decided to put the first uninitialized item in that section, and it spans that myUninitVar spans from that uninitialized section, which the tail end of is at 1F0. So if I want to be explicit here, we can actually copy this here and put 000. That's the start of the section, start of init data, and this is .data section. 1F0 is last 16 bytes of init data.data. But linker starts BSS data here, which is .bss == uninit data. my uninit var, so my uninit var, which is 152 bytes, and I'm going to use my crude ASCII graphics if you don't mind here, and we're going to actually put an up arrow and a down arrow, which is going to be our lowercase v, and we're going to do the same thing here. Fancy graphics. Look out, everybody. Oh, hello. Come on. Okay, VS Code, I appreciate that help. So eager to help. Okay, and it goes to the end of that. Let's actually calculate that. So the end of that would be, let's go hex, let's say 1F0 plus, and let's go to decimal mode and say 152. And that brings us to 288. So we'll put 288 here. And this is 1 byte past the end of my uninit var. So what we can see here is my uninit var begins at the tail end of the initialized data area. The structure itself spans from that area over into the uninitialized data area. Now, that's fine from a program loading and executing standpoint because the loader and everything, everything takes care of all that and it works fine. What Ghidra is doing here is it is actually assuming that if a structure is defined starting in the initialized data section, that it will reside entirely in bytes which are initialized in the PE binary itself. And that assumption actually fails here. And so Ghidra is unable to handle this. It thinks that the structure is fully initialized because it began in the initialized data section. And that assumption actually doesn't work here. Just because the structure begins in the initialized data area doesn't mean the variable itself is initialized from a logical program standpoint. And in this case, our structure is not pre-initialized with any particular values that we care about, but the linker happened to place it at the tail end of the area that does contain initialized variables. And there's nothing wrong with that, but Ghidra sees that, and it kind of assumes that the entire structure is fully initialized with some data, and it can't get all that data. So it can't complete handling that particular data item. And that causes it to choke on that and throw that exception. All right, I want to go back over to the assembly program, and I'm going to replace it with a slightly modified version of the program. This modified version of the program is identical to the other version. The only thing which has changed is the structure. The structure is no longer 152 bytes. It's basically a total of 17 bytes. We have 8 bytes, 8 bytes, and 1 byte. This smaller reduced structure is really pretty much going to show us the same example. It's just using a smaller structure to show that you could be more minimal with the size of the structure here. As long as you can have one structure that spans the initialized and uninitialized areas, you'll be able to reproduce this issue. So we are going to go to the command line and we're going to rebuild this. And we're going to look at the map file. As you notice, I have the map switch here. And let's go look at that. As you can see, the myinit var starts at 000 and the myuninit var begins at 1F0. Because this structure, myuninit var, is 17 bytes, it can't fit entirely in the last 16 bytes of this initialized data area. It has 1 byte that goes beyond that. Let's actually see that from the Ghidra perspective. We're going to go to the command line, and what we want to do is we want to copy the new binary, and we want to copy it to the one that has the number 2. So I'm going to copy the exe to the same name, but with a 2 added at the end here. And that should just create 2 copies. Here's the first copy, here's the second copy. And just to make sure that you're not using the old second copy, check the date and time and just make sure they're all identical. Now we go over to Eclipse. We're still in the middle of this debug session, so I'm going to press F8 to get the debugger fully running. I'm now going to go to Ghidra. Here's the error from the last repro. Going to click OK. Going to close this. Going to go over to the Ghidra main project window. I'm going to select all these and hit delete. I'm going to press I to import. Going to import the first version. Click OK. Click OK. Double click to open the code browser. Now this is located in the same folder, so symbols should already be set up. I'm going to choose yes to auto analyze and analyze. I'm then going to go to the edit menu and just double check and make sure my symbols are all set up. Yes, they are. Looks good. Going to click OK. Going to click close. Going to click save. Going to press I to import again. Going to choose the second copy. Click OK. Click OK. Open the code browser. Yes. Analyze. Okay, while we're here, we could actually look at this one by double-clicking on data. You can see here's my init var, and let's scroll down to the bottom of that variable, and let's actually right click and do expand all data. And you can see at 1F0 we have those 16 bytes that will fit at the tail end of the initialized data area. And then starting at 200 is the last byte of that my uninit var. That's the 17th byte. It's at the address that ends in 200, and that is the beginning of the uninitialized data area. So BSS, which is the uninitialized data section, that begins in the initialized data area and it finishes in the uninitialized data area. Okay, let's close this. Let's click Save. Let's highlight both of these, right click, Open With, Version Tracking. I'm going to select both binaries. I'm going to right click, Open With, Version Tracking. The original is the source. The one with the number 2 is going to be the destination. Good. Click Next. I'm going to click Run Precondition Checks. We're going to ignore the caution symbols. Click Next. Finished. Here's the source. Here's the destination. And here's the version tracking window. Let's click the magic wand here for auto version tracking. Go over to Eclipse, and we can see it's right before the error occurs. We can actually trace into this to look at the details. I'm just going to actually hit F6 to step over, and we see it through the exception. Now, we've kind of focused on where the original error occurs. Let's actually look at the loader area. Now, recall we have a conditional breakpoint in the PE loader. So let me double click on that area. And the reason why that breakpoint hasn't been hit is because it's a conditional breakpoint. So let's go to the breakpoint tab here, and here's the PE loader breakpoint. Let's double click on that, and it'll bring us to the location where that breakpoint is set. I'm going to right click and choose breakpoint properties, and we can see that it's going to break when it sees the .data section. And our program has a .data section, so that's good. But then it's going to look for the PE module that is console app.exe, which does not match the current program. So what we can do is go to the command line here, and let's grab the name of this exe. And we're going to go here to the conditional breakpoint, and we're just going to double click on that and press delete. And then I'm going to paste this in and remove that space. There we go. Now I'm going to do apply and close. I'm going to press F8 to end our prior debug session. I'm going to go over to version tracking, dismiss the error, close version tracking, go over to the Ghidra project menu, going to select all these, click delete, click OK, press I to import, going to select the first copy, going to say okay, okay, and great, it hits our conditional breakpoint during the section processing. So recall, this is the PE loader area of Ghidra, and this is the process memory blocks function, and it's stopping when we're handling the .data section. Let's go to the variables window. So where's section name? Here's section name .data, and then we go to prog up here. We can open prog up and look at the name. Where's name? And it's init uninit data section.exe. One thing we could do is let's go here. Let's type in dumpbin, because this is a Visual Studio command line window for the x64 native tools. So dumpbin is available to us. And I'm going to type in dumpbin and then init and then that exe. Let's hit enter on that. Okay, now let's recall the command line. Go over here, put a space, type in /section:/data, and we get a more detailed view of that section's information. We can see that the size of the raw data is 200 hex bytes, which is 512 bytes. That's the size of the initialized data area. And the uninitialized data area begins at that 200 point. The virtual size, or the runtime size, is 20C, which is the 512 bytes plus 12 bytes. That C, or 12 bytes, is located in the uninitialized data area. And that's the area that contains that last byte of that smaller version of MyStruct that we have in the reduced program. So going back over to the program, what I'm saying here is that this last byte here for field 3 is in the area that's covered by the C bytes there. If we go over here to Eclipse, we can see what the value ends up being, because it's going to process this section. I'm going to press F6 to go past all of these. So this is the read, write, execute, which is going to be the usual true, true, and then false for the executable. And here it gets the raw data size. We can see that the raw data size is 200 hex, or 512 bytes. We then hit F6, F6, and we can see that the virtual size is 20C. So we see 200 and 20C for the virtual size. It's no surprise, because Ghidra is getting the information from the same place that the dumpbin tool gets the information. Let's go back over to Eclipse here, and we're going to do F6, F6. I'm going to go through all this. It just created an initialized block of memory, and it's going to drop down through here. It's going to perform this calculation to subtract from the virtual size the amount of the raw data size that it just handled. That's pretty much going to be virtual size minus raw data size. So 20C minus 200 hex leaves us with C bytes in hex, which is 12 bytes in hex. And let's see if that pans out. It sure does. Here's 12 bytes, or C bytes. Great. Now it's going to take the address that the data section began on, and let's look at that address. If I can find address in here. Here's address. So we expand that, and we see 14000 4000. That's the beginning of the data area. We've already processed the first 200 hex bytes. So this is going to add raw data size, which is 200, to that address. That makes sense. And that'll be the next address that we need to process. So let's hit F6. We hit F6 and we can see the address is incremented by 200 hex bytes. That's the beginning of the uninitialized data area, which happens to be sort of in the middle or in the midst of the .bss section, which is physically included in the .data physical section of the PE executable. Let's press F6 and F6. And we can see it's calculating what the data size is, and that's just simply going to be the 12 bytes, as we saw before. And now it's going to create that uninitialized block. So we'll do F6, and it creates that uninitialized block. So I know this is probably clear, but just for clarity, everything we just looked at just now here, all of this happens on loading or importing those binaries into Ghidra as part of Ghidra taking that external world of PE executables and turning it into the abstract world of its internal databases and structures. For the case of PE modules, it goes and does all this walking of the sections, so to speak. And as it walks all these sections, it calculates all the different data areas and creates different subblocks and so forth. So what we just noticed is it created 2 blocks of memory for the .data section. One block is the first 200 bytes, which is initialized. The second block is the uninitialized data. There's nothing wrong with having an initialized data block and an uninitialized data block. However, it just so happens that the build tools placed a structure at the tail end of that initialized data block, and it spans over into the uninitialized data block. And that's just something that Ghidra did not expect. So generally speaking, we have enough information where we could report this issue. We also have enough data where we could probably apply our own workaround if we needed to until it was officially fixed. Okay, I'm going to press F8 to finish off this load. Looks like it's finished. Let's go over to Ghidra. Okay, I'm going to click OK on this. And what I'm going to do is just delete this. And I'm going to exit Ghidra. That's going to end the debugger. I'm going to actually exit Eclipse. I'm going to clear the command prompt here. And I'm actually going to go into the Ghidra repo folder. Now, I happen to know a fix is available for this problem. So the first thing I want to do is I want to go to the main or master branch for Ghidra. So one thing I can do is just do git branch. And git branch will show me the branches I have locally. And it looks like Ghidra uses the master as the main branch. So I'm going to go and check out master. And I'm going to do log and make sure that the head is the tip of master. Looks good. Clear the terminal window. And the fix for this issue is in this git commit here. So if I do git log, we can see there is a merge commit here, and it includes this fix here. PE loader now pads initialized memory blocks with 0 instead of creating additional uninitialized block. Also improve byte source column of memory map. So let's go ahead and create a branch that has as its tip that particular commit or fix. So I'm going to say git and checkout -b. I'm going to name the branch uninit-data-fix, and then we're going to specify the commit with the fix to be the tip of this new branch I'm creating. I'm going to press enter, and it looks like it was created. That's great. We have a new branch here called uninit-data-fix, and the tip of that branch includes the fix for the issue. Now you might ask, why don't I just use master? And the reason why, actually, there's 2 reasons. One is I wanted to use this approach for illustrative purposes. Another one is there happens to be a build issue. In the last week here, there was a build issue in master that they were planning to fix. And I don't know if it was fixed. And I could have included the workaround in this walkthrough. but I kind of didn't want to do that. This actually allows us to have a hybrid where I'm essentially using master, but only up until the commit that fixes the issue. And that just so happens to ignore a lot of later commits, including the one that has some kind of build error when you're on Windows. Yes, I probably could have cherry picked here, but rather than assume that that would have worked and that there were no dependent commits and whatnot, I just thought this would be the simpler approach. Okay, with our new branch set up, what I want to do is first let's run a clean. All right, with the clean complete, I'm now going to run the command to update the dependencies. And now I'm going to run the Ghidra build command to test the build from the command line. All right, if we do ls here, we can see here, this is the build that we finished yesterday. And this build right here is the one that we just finished building, and that includes the fix for the issue we've been debugging. Instead of extracting that binary and running it directly, let's prep the Eclipse environment with the updated source code, and let's run Ghidra in Eclipse, and we'll test it from there. Now let's run the Gradle prep dev Eclipse build natives command. So we'll paste that in, and I'm going to hit enter. Okay, prep dev was successful. Now let's run Eclipse. So I'm going to run Eclipse from the command line, and I'm going to click launch. We'll use the same workspace. I'm going to go to Window, Perspective, Open Perspective, Java. That opens up Package Explorer. I'm going to select and do Control A. Going to right click, and I'm going to do refresh. I'm also going to go to the project menu and choose to clean. Everything is selected. I'm going to ensure that clean all projects is selected, and I'll perform a clean. I'm going to ignore this clean error, and I'm basically going to click down here to open up the detail % bar while it's building, and I'm going to let the build complete. All right, with the build complete, I'm actually going to go to Perspective, Open Perspective, Debug. I'm going to click on the Debug dropdown and choose Ghidra, and it looks like it's starting up. I'm going to press I to import. It defaults to the home directory, so I'm going to type in C:\/ Ghidra dev. I'm going to hit enter. And our binaries, let's use the ASM binaries. So we'll pick the first one and import. Click OK. Okay, it looks like it hit a breakpoint. Let's see what it's doing. Oh, there's an invalid condition. Let's actually look at that. This condition is invalid because the source lines have changed. So our breakpoints were already in this workspace, but we've changed the source code to updated source code, and the lines are offset. So the section name doesn't actually exist on the old line. So what we're going to do is I'm going to copy our, copy our expression here in the conditional. So we're basically going to create the same breakpoint on line 661. Because what used to be line 660 with the old source code is now 661. And so section name technically doesn't even exist yet until this line 661. So I'm going to double click here to create the breakpoint, right click, properties, and I'll check conditional. I'll paste in the conditional. I'll click apply and close. I'm going to delete the old breakpoint, right click, and there should be a toggle breakpoint, I guess that'll delete it, and it's gone. If I just hit F8, it'll step one line and actually hit the breakpoint with the condition. This is a good way to test it. Let's test it out, F8, and it works. Now our other breakpoints might be offset on the wrong lines as well. We can actually select breakpoints, and we literally could go to the enabled breakpoints and double click and look, this one looks good. And let's click the other one. That looks good as well. This one's disabled, but we can look at it really quickly. Well, that's good too. PE loader, we just fixed this one. Uninitialized submemory block, and we see the constructor is located in the same location and the breakpoint is at the right line there. That's good. All right, so I'm going to click the top of the stack here to get back to our execution point, and that's the location of our updated breakpoint for this PE loader conditional breakpoint. And we just hit this breakpoint successfully, which is really nice. Now what we can actually do is double check things in the variables window. So let's look at prog. Here's prog, and the prog name is the name that we're expecting for this binary. And let's go look at section name. Section name is .data. That's good. We can see that address is the start of the data section. All right, let's hit F6 to step, and I'm going to hit F6 to step through here. We're going to go down to after these variables are set up. Raw size is 512 or 200 hex bytes. The virtual size is 20C. So that includes the raw size plus the extra 12 bytes that go into the uninitialized section, or what used to be the uninitialized section. We're going to step on down here and kind of see how this code handles things. So this is going to go in here to create a block here, and this block is 512, and it's checking here and checking here and checking this. And now it's going to subtract raw size from virtual size, and it's going to increment the address. And now it's dropping down here. It's going to do the data size calculation, and let's step down here and look at this. If block is not equal to null, it's actually going to create this thing called padding block, and it's going to do that by creating an initialized block. So what it's going to do is it's going to create a 12-byte initialized block following the first 512 bytes of the initialized section. So there's going to be two blocks, one block that's 512 bytes and it's initialized, and then another block which is 12 bytes, and that will be initialized. That following block is no longer going to be uninitialized, which means that other code won't throw an exception. Let's actually step down through here, and we can kind of see it's creating this, padding block. Let's see if we can see anything in that padding block. Here's the padding block, here's the sub block, and we can see this sub block is a buffer sub memory block. All right, let's press F8 to run the debugger, and the debugger is running. It's not at a breakpoint, so that binary has been loaded. Let's go back over to the Ghidra project menu. Let's click OK to accept. The Ghidra project window. Let's double click to load this in a code browser. It's going to ask us if we want to auto analyze. Since this is my first import after changing the environment around a little bit, I'm going to dismiss this. No, don't analyze. And then I'm going to go up here to the edit menu, choose symbol server config. Let's click plus and add the Microsoft public symbol path. Let's click plus and add a directory. Going to click the ellipsis. Going to type in C:\Ghidra -dev. Going to drill down here into a sem. Click choose. OK. OK. I'm going to validate that it can find the PDB by going to load PDB. We see a green check here, so it looks good. I'm going to click load. I'm going to press A to analyze. Click analyze. We're going to wait till the analysis is finished. Looks like it's finished. I'm going to dismiss this window and choose to save. I'm going to press the I key to import, and I'm going to import the second copy. Going to choose OK. OK. Going to double click to open the code browser. Okay, we know the symbol paths are set up correctly. I'm going to say yes to auto analyze. Analyze. Okay, it looks like it's finished. I'm just going to sanity check the symbol config. Okay, it looks good. That's what I expected. Let's click OK. Okay, let's dismiss this and click save. Let's highlight both of these, right click, open with version tracking. We're just going to make sure that the source is the original and the destination is the one that has 2. Looks good. I'm going to click next. Run pre-condition checks. We're going to ignore the caution signs. Next, finished. This is going to open up the 2 code browsers. Here's one for the destination, here's one for the source, and here's the version tracking window. Let's click the magic wand to begin the automatic version tracking. Looks like a breakpoint might have been hit. Let's go to Eclipse. And sure enough, this is that breakpoint that calls into getBytes. Let's actually look at A-data. So A-data is here. Yeah, that's at offset 1F0. Let's look at the base data type, and it is a structure, and the name is my struct. Okay, let's use F6 to step over that line and see if we end up in this catch here with the error, or if we get past it without any errors. So I'll press F6, and it looks like we flow nicely without any errors down to the subsequent lines. I'm going to press F8 to continue running the debugger. Okay, the debugger is running. Let's go back over to the version tracking window, and it looks like version tracking is working successfully. All right, everybody, that's it for this video. If you like this video, I hope you'll click like, and if you want to subscribe to this channel, click the subscribe button down there. I'd be super happy about that. Other than that, as always, be well, be safe, rock it out, happy debugging, happy eclipsing, happy Ghidra-ing, and all the above, times 10, times 100, be well. All right, everybody, take care. All right, thanks. Bye-bye.